Now I am. All right, everyone. Welcome to the Math 132 review session number 1. This is being presented by the Mathematics and Statistics Students Center. I am Anthony Shamango. I am the Assistant Director of MS3 Center. Rafael Gonzalez is our Director. I just have some directions regarding our review session, and then we'll begin looking at the problems, namely how to solve them. So for those that are meeting with me here in person, do you think that it's better that I have the screen vertically, or would you prefer it being horizontally? Horizontally? Okay, we'll do horizontally. Sorry, why am I echoing? No, don't unmute me, Rafael. You make me echo there. I have to speak directly through the iPad, so that way I don't echo. Sounds good, Rafael? I'm gonna speak through my iPad because if I unmute the other Zoom from my other account, it echoes. Okay, my bad about it. So yeah, I'll probably keep it this way. I think for those that are in the Zoom meeting, I think you will get a better view as well. Okay, so here are the directions for our workshop. The purpose of review session number 1 is to prepare students for their upcoming exam. Namely for students that are enrolled in Math 132, it's most likely exam number 1. Your exam number 1 should consist of topics starting from the very beginning of class all the way up to probability. Now, every instructor teaches differently, so I don't know exactly where they are up to in their course, but I'm covering, based on the Pearson My Lab, I'm covering basically chapters 1 through 4. So it's everything from the beginning all the way to conditional probability.
This is for the people who have like the class on Thursday, 9 a.m., or is it like for different?
This is for all students enrolled in Math 132. That's right. So it's not just for one specific section of Math 132. It's for all sections.
So I got confused because on Thursday, like 9 o'clock, I have to do the class until 12. There's like no one.
Right.
And most of the time you have to do it yourself. And
is that a hybrid class with Professor Lackett?
I think it's either.
Because if that is the case, then I think the topics that we'll do today, you've already seen them, so you should be fine. Okay.
Seen them because no one's in the Zoom class one at a time. And I don't know. I just have to figure it out myself.
Okay. Well, we'll see what you know and what you don't know. Okay. So during review session number 1, we'll discuss and explain how to solve problems in the following table summarized to the right. So again, these topics that I have shown in red, introductory to statistics, descriptive statistics, and probability, they from our textbook, the Pearson's version Triola, it's chapters 1 through 4. Okay. And the breakdown of each topic is there. We're going to look at statistical and critical thinking, types of data, and collecting sample data. That's covered in the first chapter. Chapter 2 and 3 is where you do all the descriptive statistics. That starts with the frequency distribution, histogram, stem and leaf plot, scatter plots, correlation, regression, mean, median, mode, mid-range, range, variance, standard deviation, range rule of thumb, the empirical rule, 5-number summary, and box plots. After that, we'll look at probability, the basic concepts of it, the addition and multiplication rules, complements, and of course, conditional probability. So the problems, the way I have it broken down, I have it to the most part sequential, where I start with introductory statistics and I go into descriptive statistics. But the probability, the last few set of problems, for each topic, the breakdown that I gave you, those problems are not in specific order. Okay. All right. So I am going to begin going over the solutions. So for those that are sorry, I was going to pull this chat up on the side. So that way I get to at least read some of the things that probably will be there. I'll just put it here towards the bottom. So feel free for those that are in person or there in the Zoom meeting to share your opinion, any questions or any answers that you think that you know of. Okay, so the very first problem number 1, states to determine whether the study is an experimental or observational study, and then determine a major problem with the given study. So part A states that USA Today posted this question on their website. Should Americans replace passwords with biometric security, namely like fingerprints? Of the 1,510 Americans who chose to respond, 75% of them said yes. So for part A, do you think it's an experiment or observational study? Observational? Why do you think it's observational? Well, you have to be a little bit more specific. What do we know about the observational studies that's different from an experimental? Yeah?
They're not giving them any treatment.
That's right. The researchers are not giving the our sample size of the 1,510 Americans any treatment, right? The researchers essentially do not attempt to modify the individuals in the research. So let's write that out. So it's observational because the researchers do not attempt to modify the individuals of the study. Essentially, we're answering this question by just basically explaining the definition of observational studies, right? We're just using that definition, right? The researchers do not attempt to modify the individuals. They only observe and record the data. Okay, so we answered the first part to part A, but now what's wrong with this study? What is wrong with it? It's voluntary.
Only a question, not a demand.
Well, not necessarily.
Would you like to have replace your password with biometric security? It's only a question of would you like to do it, not you will do it, or
Well, it's a survey, right? It's a question on their website, so it's a survey. But namely, what we know about the survey is that it's a voluntary response sampling. And what do we know about voluntary response sampling? Why is it not good for your study? Yeah?
You can be biased.
Yeah. Voluntary response sampling leads to biased results. And by the way, what key word gave it away that it's voluntary? The word chose. All right, so let's underline that word. That word chose emphasized that, again, the sample, they voluntarily responded. So we say that what's wrong with it? Well, it's voluntary response sampling. Which leads to biased results. And that's it. That's all you could write for part A. Is there any questions to part A? Okay, let's look at part B. It's a little bit of a mouthful, but we'll go through it. It states that a researcher for a consortium of insurance companies plans to test for the effects of drinking on driving ability by randomly selecting 1,000 drivers and then randomly assigning them to two groups. One group of 500 will drive in New York City after no alcohol consumption, and the second group will drive in New York City after consuming 3 shots of Jim Beam bourbon whiskey. Is this an observational or experimental study?
Experimental.
It's an experimental study. Why do we, or how can we tell automatically that this is experimental? What do we know that the researcher did to the individuals? Yeah, Edwin?
They trying to modify their behavior.
Yeah, they definitely try to modify their behavior. I think that was one. I sorry if I mispronounced your name. Yes, you're correct. They definitely try to modify their behavior. But more importantly, what else do we know about the individuals?
Like one group didn't drink alcohol and the other.
That's right. There was one group that didn't drink alcohol and one group that drank the alcohol. So though there are specific names for those groups, right? The one group that were essentially drinking the alcohol, if the group that's drinking the alcohol, is that going to be the control or no?
The 500 will be the control, and the other one will be the modified group.
Well, the modify, or there's another way of saying it. There's a control group, which are those that are not drinking the alcohol, but the other group is called what? Anybody want to take a guess? The group that's drinking the alcohol is called the treatment group, right? So there's a treatment and a control group. So let's write that out. So for part B, it's definitely experimental. And just going by the definition of an experimental study, we can say that it's because the researcher applies a treatment. Now, I don't know if this is actually a treatment, but the researcher applies a treatment to some individuals, namely those that are consuming the alcohol. And the remaining individuals are placed in the control group, those that are not drinking the alcohol. So I'm just writing this out. In a control group. Okay, that's it. You just basically apply the definition of an experimental study. You should identify that there are 2 groups, one getting a treatment, the other is not. Okay, now what's a major problem with this study? First of all, let's try to clarify something. Were the individuals in either of these groups voluntary responded, or did they volunteer? No. How do we know that they're not being volunteering? Yeah, that's right. So we hear, because it states that the individuals are randomly selected, we know that definitely voluntary goes out the window. They didn't choose to be in one of the groups. So what else can we say? What's a major problem with this study? Think about it. This is where you have to actually think about it logically. What is technically our treatment again? Alcohol. And what do we know about drinking this alcohol? What are we doing? It's hindering our abilities, namely hindering our ability to drive. So is this an ethical study? No, it's an unethical study. So that's the main issue. The experiment here is unethical. The experiment is unethical, and it's also illegal, right? Is it legal to drink and drive? No. So it's unethical and it's illegal, right? So this was a case of where you actually had to think about the situation. Well, how do we know it's unethical and illegal? Because if we drink and drive and we sort of make an accident, it can cause what? It can cause, no, I said, if you drink and drive and you're making possibly death, or before death, you could say injury. Yeah. When you say underage, you mean under the age of 21?
Yes.
Well, the problem never, yes, never specified whether or not if these individuals were under the age. But yes, more importantly, it's illegal and unethical because, again, it can cause injury or possibly death to innocent people. Yeah, Edwin, question?
You can also say that they are forcing people to do that because maybe.
Yeah, they are, right? That's what the treatment does. That's what a treatment does. Whoever's in the treatment group, you're essentially forced to take that treatment. So the experiment is unethical and illegal. It can cause injury and death. All right. So do you think that this is actually an appropriate experiment? No, this is definitely not an appropriate experiment. In fact, we could just make a side note. I'll put this in red. What the researchers could have actually done in this case is use what we call a retrospective study. A retrospective study might be a better approach because in a retrospective study, it's an example of an observational study where essentially the researchers study past results. So I'm just going to write that as a side note. Then I'll entertain any other questions. And if there's no other questions, we'll move on to problem 2. So let me just write this note down. So a retrospective study might be a better approach. In a retrospective study, the researchers look at past results, right? Study past data. And then the researcher makes their recordings or their findings, yeah? Yes, I think, what, my slides? Well, we have it recorded, and after the meeting, it will be sent out to all Math 132 students, the recording. You're welcome. All right. Any other questions with problem 1? We're good? Okay, let's move on. And in the Zoom meeting, those on Zoom, or do you guys have any questions?
Nope.
Okay, so I'll continue. So let's look at problem number 2. For problem number 2, it states that for the following study, we want to identify the population, the sample, the statistics, namely the sample statistics, and the parameter, right? So before we look at population and sample, just note that when we deal with statistics, one way of knowing what goes for which, what letter does statistics begin with? It begins with the letter S, so it's associated to a sample. On the other hand, when you look at parameter, it begins with the letter P, and it's associated with the population. Okay, now here's also a good picture to draw regarding a statistical study. Usually after you formulate your question at hand for your statistical study, or whatever your research is based upon, you need a target audience or target group. That is essentially your population. However, what you've learned in class is that the population can be very large. And in order to do your statistical study, you need a good representation of your population. So there are different ways of choosing your a good representation of your population, namely a subset of it. You could do randomly selecting individuals. You can do convenience is not always the best. There's other ways. There's called systematic, that usually what people use for when they're dealing with data that they could just pull from computer basis. But long story short, after you get the population, you then target a sample. a good representation of the population. From your sample, you're pulling data. That data is your statistics. From your statistics, you then use, which you'll see later on in this course, we're going to use inferential statistics based off of our the statistics that we gathered from the sample to get our parameters. And when we get the parameters, we can make conclusions regarding the population. So this little drawing that I have here should be helpful regarding identifying a population, a sample, statistics, and parameter of our of any statistical study. Okay, so for problem number 2, so I'm just going to swap the color real quick. It states that in a study of 8,505 US high school students, 16 years of age or older, 44.5% of them stated that they text while driving at least once during the previous 30 days. Right? That's our statistical study. So we got to identify population, sample, statistics, and parameter. So what do you think will be the population for this study? Yeah? 8,505. Do we agree? Is that going to be our population? 8,505 US high school students, 16 years of age or older? No, right? It's not. Instead, the population, yes, Lauren. Lauren mentioned it in the chat. The population is the key word when you're describing population. It's all of the individuals of interest. So who are the people that we are interested in? We're interested in the US high school students, 16 years or older. So our population is all of them. Right, so again, I just want to emphasize that when you're talking about a population, the key word is all. It's all US high school, I'm just going to abbreviate this, US high school students, 16 years or older. Okay. Population is everything or all the individuals or objects of interest. Very good for those that were in the chat. What about our sample now? Yeah.
45% of them stated they texted right.
Unfortunately, no, that's not going to be it. We want our sample. The 8,505, right? The sample is a subset of the population. Right, so I'm gonna abbreviate. I think I could fit it. So our subset is our sample is a subset of the population. So if the population is all of the US high school students 16 years or older, the 8,505 is just a subset of it. So that would be it. So you say that your sample is 8,505 US high school students, 16 years or older. Okay, now from our sample, did we obtain a statistic? Yes, we did. What is our statistics in this problem? Yes, right, so we just want to, when I'm writing out, by the way, the population, sample, statistics, and parameter, I'm writing out sort of like as a phrase or a sentence. That's how you usually describe them all. So for our statistic, we just can't write 44.5, but what we can write is 45.5% of the sample stated that they text while driving at least once during the previous 30 days. Okay, so here's our statistic. So we say 44.5% of the sample stated they text while driving at least once during the previous 30 days. That's right. Hello, O'Neill.
Hi, Mason. Hi, everybody.
Okay. Now, we got our statistics. Now let's see if we have a power meter. In this problem, did it give us a power meter? Did it give us any numerical value that describes the population? In this problem, did we gather or did we obtain any numerical value or any information that describes the population?
Just at all.
Say it again.
Just at all.
It just said all. Yeah, O'Neill.
I agree when we analyze the population, we say all the members of the.
Yes, that's right. We already covered the population part. Well,
Yes.
not necessarily. The 16 years or older is not necessarily. I mean, it's part of the. It's part of the population, right? The group of interest are high school students that are 16 years or older, right? I do agree with that, but no. Text while driving, no. No. The parameter is the tricky part. And here's why it's the tricky part. When you're doing a statistical study, again, in order to go from statistics to parameter, we have to do what we call inferential statistics. Now, in our statistics course, we're not up there yet. We're not, or for majority of the courses, we're not there yet. We're not doing any confidence intervals. We're not doing any hypotheses testing at the moment, right? That comes at towards the very end of your course. So without running any inferential statistics, there's no numerical value that we can gather at the moment for the parameter. But we can still describe a sentence regarding the parameter. So it's something like what Lauren is mentioning. Is a parameter the relation between the sample and the total population? Almost. I just want to clarify that we use the statistics rather, right? There's a relation between the parameter and the statistics. The statistics, we gather that information, such as the 44.5% in this example. We're going to run some inferential statistics on it, and then we're going to gather a numerical value that will give us a parameter, right? So in general, for the parameter part, we can just say that it's the percentage of your population which we denoted above earlier, right? It's the entire, all of the US high school students 16 years or older, right? Whatever that percentage is, when we run our inferential statistics, that stated they text while driving at least once during the 30 days. Right. The key phrase here is that we begin by just saying the percentage, because again, we don't know what that percentage is. We have to do an inferential statistics, which again comes later on in this course. Is there any questions on that? Go ahead.
What slides is it? What chapter?
I'm basically covering chapters 1 through 4 of the textbook. But these problems, some of them were from the textbook, directly from it. Some of them I used from previous courses. That's right. So these are my own slides. Yes. Yeah, O'Neill?
Listen, I'm here and I'm confused something.
Uh-huh.
What is that here?
That chart?
Yeah.
That chart, you came in a little late, O'Neill, but I'm just gonna restate it. And then if there's no other questions, we'll move on. Basically, there's a what that chart is showing you is that when you're doing a statistical study, after you figure out your question at hand regarding your study, you have a target audience. That target audience is your population. From that population, you want a good representative sample. So you have to apply some sort of sampling method. Then to go from sample to statistics, you're just gathering data from that sample. Once your data is gathered and it's organized in a specific way, whatever calculations you did, like for example, finding mean, median, mode, mid-range, for instance, then you could run inferential statistics on it or apply inferential statistics to gather the parameters. The parameters are used to make conclusions about the population.
Okay. So that's some elements we use to analyze the population.
Yes, yes. Alrighty. Any other questions regarding problem 2? Okay, I'm gonna pick it up a little bit. Let's look at problem number 3 now. Oh, wait, there was another question. That's right. In the chat, I'm sorry, I can't pronounce your name. Gertrude? Gertrude? I'm so sorry. Can you say that the parameter? Yes, it's the percentage of whatever our study was regarding. So it's going to be the percentage of the population that they text while driving at least once during the 30 days. But we just can't say that it's exactly 44.5. We won't know that for sure until the inferential statistics is being run. Sounds good? Okay, cool. I'm sorry about that, by the way, about your name. Okay, problem number 3 states classify each variable as either discrete, continuous, or neither. So let's try to give the answers and then we'll write out the explanation for each. So part A states the number of donuts sold each day at Donuts Heaven. So for part A, is it discrete, continuous, or neither? And why? Yeah?
It's discrete.
Why?
Because you can measure and count the amount.
Careful. You can't say both measure and count. It has to be one. You can count. That's it. Part A, it's discrete because that data set there is countable. And countable implies that, again, now that the data can only take on specific values. So that's discrete. Let's look at part B. Water temperatures of 6 swimming pools in Miami on a given day. Continuous. Why?
The water temperature on a given day, like maybe it's on Monday, you gotta check the temperature and for each of every one.
What is that called? What are you doing?
You're counting each.
We're not counting. You're measuring. That's right. That's correct. Part B, we say that it's continuous because it's uncountable, right? The difference between discrete and continuous, yes, I write the word countable, then uncountable. But when I say specifically uncountable, I'm talking about a measurement, right? For example, if you want to measure your height or your weight is actually a good example. Anybody ever jump on the scales and they see that their weight usually goes
Below zero.
No, well, it can't go below zero.
Well, wait.
No,
Sometimes
well-
a little arrow go below, so you're gonna get.
Well, no, sometimes that decimal number, it jumps.
Oh, okay.
It oscillates between like 2 or 3 numbers, right? Like for example, if you're like 133, but then on the scale it goes 132.9 or 133.1, right? Though it's a measurable. Right? When you're talking about, for example, the number, the total grams in a donut, that's continuous data set. But if you're actually counting the number of donuts, like, you know, a key word there was the number, you're counting it. In part B, water temperatures, well, in order to do some sort of calculation with temperatures, you're doing a measurement. So it's continuous. And a continuous data set, yes, you have an infinite number of data values. Another way of phrasing it is saying that data can take on any values, right? Discrete is only specific values. Continuous, data can take on any value in an interval. All right, very good. And lastly, for part C, the colors of the baseball caps and Foot Locker. The Yankees won, by the way. The guy, Anthony Rizzo, he got my first name. He's like, that's the only reason why I like him, because he got my first name. Smacked that 2-run home run. It was a good one. But anyways, colors of the baseball caps and Foot Locker. Is it discrete, continuous, or neither? Neither. It is neither.
Counting the number of baseball caps, but it doesn't say the same thing as baseball.
That's right. If it said the number of baseball caps, it would have been a discrete data set. But because we're talking about colors, what do we know about colors? What is colors actually there you go. It's qualitative data. Very good. It's neither.
And there could be new colors every time, so you won't know which one's which one.
No, we're not doing any counting. You gotta take that word counting out from your sentence. We're not counting baseball caps. However, what we're doing is we're looking at the colors of the baseball caps. The colors are qualitative data because you're splitting all the baseball caps in categories, right? For example, blue baseball caps, red, orange, black, white, etc. Now, if you actually want to create a frequency distribution, then yeah, you can count the frequency of each baseball cap, but we're not doing any counting at all. So neither, because it's qualitative data. And again, qualitative data, we know that we're looking at attributes, labels, or even categories. Any questions to problem 3? So like almost for like I think up to like problem 4 or 5, we're just doing straight up definitions. But that's all chapter 1 was about of our book. It's just definitions. Okay. Can I continue? All right. Let's look at problem 4. So problem 4, I think this is where my definition starts to end. It states, determine which of the 4 levels of measurement, nominal, ordinal, interval, and ratio, is most appropriate for the data below. So I know that usually when this section is covered in our textbook, usually, I don't know about the other instructors, but for me, I know that I give the definitions, I show some examples of it, and then we move on. But here I give you the hints, which is shown to the right. And we're just asking whether part A through D are going to be nominal, ordinal, interval, or ratio. So let's begin with part A, body temperatures in degrees Fahrenheit. Look at your 4 definitions. We have nominal, ordinal, interval, and ratio. Which one of these definitions applies to part A? Let's start with nominal. Will nominal make sense? Or nomial, sorry. No. So we can for part A, we know it's not nominal. What about ordinal? Can body temperatures be possibly put in some sort of ranking? Yes, it can. Yeah, you can put body temperatures in a ranking, right? For example, my body temperature could be what, like 97.1, but you could be 97.2. Is that a ranking? Yeah, there's some sort of rank or order to it. Namely in temperature, right? When you look at cold versus hot, right? We know that the colder temperatures, they have some sort of, they're going to be the lower Fahrenheit in Fahrenheit is the lower degrees, whereas the warmer or hotter temperatures, they're going to be the higher value in degrees. Okay, so ordinal could possibly make sense. Let's look at the other two, interval and ratio. Do you think that this could also possibly be interval? Can you put the body temperatures actually on a number line? Yeah, right. Any sort of measurement. Remember, we talked about temperatures earlier as a measurement. Any continuous data can be written on an interval. So the thing about interval data, at the interval level, it states that data at this level do not have a natural zero starting point. So when you look at temperatures in general, does it naturally start at 0 degrees Fahrenheit? Can you go possibly below 0? Yes, you can. You can go possibly below 0 degrees, right? If you have -5 degrees, probably like in Canada, for instance, in the winter, they could go way lower than that. There's no essentially natural zero here. There's no starting point when you're doing a measurement in terms of body temperatures. So that's the difference between interval and ratio. Ratio, there is a natural zero starting point, but for the interval, it does not have that natural zero. So therefore, the best result for part A, the most appropriate for this data, should be the interval. Again, there's no natural zero. We can't say that temperatures begin at 0 degrees. Okay, look at part B, ratings of 10 documentaries using a scale of 0 to 5 stars. Is it nominal? It can be, because it's a label, right? If you think about it, those 0 to 5 stars, those are actually labels, or you can separate the documentaries by, say again? By categories. That's right. That's correct. Can the data be ordinal? Yes, it can. Why can it be ordinal?
It's an order and rank.
That's right.
You're breaking like all the reasons.
That's right. So for this problem, it's definitely ordinal. So when you're looking at any, so this is just a little note. Part B is qualitative. And it's possible that when you deal with qualitative data, that it can be nominal or ordinal. Because there are some categories, namely like our scale of 0 to 5 stars, that have these characteristics, right? If you rate a documentary of 0 stars, then we're just saying that documentaries suck, right? And if it has a 5 star, then you say, well, that's a perfect documentary. It's awesome. I would recommend it to people. So for part B, it's ordinal. Okay, but just keep in mind qualitative data. I think I spelled qualitative wrong. Let me just double check. Yes, I did, but it's okay. No, I think I did spell it right. No, we did. We're good. So yeah, part B is called ordinal. Okay, part C, types of restaurants. That's nominal because those are categories. Now, if I said favorite types of restaurants, would it be nominal? No, it would be ordinal because you're actually going to be ranking the type of restaurants. If I were to use the word favorite in front of types.
Doesn't like ordering or numerical significance. So
Yeah.
It's not like some number.
Right. You're actually putting a positioning on each restaurant, right? Where, like, for example, the very first restaurant you would have most likely mentioned first, you know? What about the lengths of prison sentences of randomly selecting subjects convicted of auto theft? It's a ratio. There's actually a natural zero there, right? Let's say that hypothetically speaking, that those randomly selected subjects, they beat the case. If they beat the case, then do they do any censusing at all? No, they're not. They beat the system. And that would be it, right? So again, nominal and ordinal nominal is when you're dealing with qualitative data. Ordinal can sometimes be qualitative, namely when you're taking categories and you're ranking them. Data in the interval or ratio or quantitative data, but just keep in mind that at the interval ratio, there is no natural zero, whereas in the ratio, there is. Are we good? Any questions? Okay, let's look at problem number 5. So I think my definitions are over now. We're now up to essentially chapter 2 of our Pearson book. So in problem 5, it states identify the lower class limits, upper class limits, class width, class midpoints, and class boundaries for the given frequency distribution, and also identify the number of individuals included in the summary. So there are a few things that we have to do here. So what I'm going to do is I'm going to do some of it on this screen, and then I'll use the blank screen to write out some of the other answers. Namely the answers that I think are just using definitions. We can figure them out. Namely the ones that are not that heavily calculated. For example, how do we find the lower class limits? Or, sorry, what would be our lower class limits? It won't be your frequency. What are the lower class limits for this data, for your frequency distribution? Are we actually looking at the frequency column?
No.
No, we're actually looking at the first column, basically the column that consists of your classes. So yes, we're looking at the column that talks about the service time. So your lower class limits are going to be, well, if you look at these values for your classes, is it going to be on the left values or the right values? The left values. So you list them in order. So we have 30, 70, 110, 150, 190, 230, and then lastly 270. So those are your lower class limits, right? It's basically the left values for each of your individual classes.
So the upper class is the right side.
That's right. The upper class limits have to be the right side values. So the upper class limits are the values of 69, 109, 149, 189, 229, 269, 309. Sorry, that was the last one. Okay, yeah, O'Neill,
Mister, I'm confused about something.
go ahead.
So the frequency is how many times we had the number?
The frequency is the number of data values that belong in each class. For example, in the first class where you have 30 to 69 seconds, that's the service waiting time, there were 2 people that essentially waited 30 to 69 seconds.
So basically,
It's the number of data values that falls in a class.
Yeah, but
That's the definition.
The number between 30 and 69.
Say it again. It's a number. There are 2 values that are between 30 to 69. Or possibly there's a value at 30, there's a possible value at 69. We don't know what those values are because it was never given. We were only given the table. We weren't actually given the individual values, okay? It was just assumed that there are 2 values in that range. We don't know what they are. They never told us, okay? But the definition of a frequency is the number of data values that goes into that class.
I have a little question. If we change that with only one line of the number, for example, have only the number in the left. So the frequency in this example is how much played before, how many times we have the same number.
Say it again.
For example, if we change this to another number like 1, 2, 3, 4, 5, and continue with another number, the frequency is how many times we have this number before?
Not quite. No. We'll have to look at that. We'll have to look at that separately, because if the thing is, I'm providing you the definition of a frequency. Yeah, Edwin?
You can also say that the lower class is the smallest value, the small value.
Yeah, that's what it is. The lower class is the smallest value of that belongs in each class, right? But to answer your question, O'Neill, and again, I'm going to move on after this. The frequency, again, is the number of data values that falls in our class, in each individual class. This problem never tell us what those values were. But if I had the number, let's say 281, where would 281 fall under? Which class? You're getting a point, you got to tell me. Which class will it go in? Yeah, it will go into the one that was 270 to 309. So if I had that value 281, then I would have tallied it, right? So if I already had 3, then I would have changed it to 4, because I would have had 3 tallies there already. The 281 would have been the 4th tally, the 4th value that went there, okay? I have to move on from your question, O'Neill, but if you want to work one-to-one, then we can after my session, okay? All right. So that's the lower class limits, the upper class limits. Let's look at class width. What would the class width be?
40,
Yeah, how did we get 40?
you can subtract an upper class limit minus the one before.
Yeah,
The lower class limit.
that's right. So the class width here is going to be actually 40. The way that we actually compute 40, you don't take the difference between the lower, any lower class limit and upper class limit from a particular class. Instead, the way that this is done, I'll write it in red. You subtract any 2 consecutive lower class limits. So for example, if I took 70 minus 30, 70 minus 30 is equal to what? 40. I don't have to just use these 2 lower class limits. I could have used somewhere around here. What's 230 minus 190? It's still 40, right? So you can use any 2 consecutive lower class limits. Okay, so that's our class width. Now we have to find class midpoints and class boundaries for the given frequency distribution. But before I do that, before I use the next slide, let's identify the number of individuals in the study. So if you want to identify your number of individuals, that is your total frequency. So one way that we can write the total frequency in notation wise, just in case if you probably see it, let's say on your exam or on my lab, the total frequency can be written as follows. Anybody know what that letter stands for? There you go. It stands for the sum. It's the Greek letter called sigma, and it stands for the sum. So it's the sum of f, where f is your frequency. So the sum of f, the sum of our frequency, or your total frequency, well, you just add up the frequency in the second column, right? You take 2 plus 6 plus 12 plus 23 all the way down. So if we add that up, what do we get? Here you might actually have to use a little calculator. Yeah, go ahead. Somebody said the answer.
66.
Is it, say it again, 66 or 56?
66.
That's right. It's going to be 66. Okay, so we got our total frequency. Okay, so we just need to do class midpoints and class boundaries. What is the formula for finding the class midpoints or finding a class midpoint for a class? Yeah.
Upper class limit plus lower class limit divided by 2.
That's right. So I'm going to write out the formula. So for the class midpoints, I'm just going to call it CM for now. It's equal to upper class limit, UCL, plus the lower class limit over 2. All right, so we're going to go in order. For the first class, from 30 to 69, well, we take those two values, add it up. You can do 30 plus 69 or 69 plus 30, you still get the same result. If you add it up, then you divide by 2. Well, what would that be? 30 plus 69, then divide by 2. 49.5. 49. There you go. So we got the first one.
Wait,
Let's look at the next class. Yeah?
How are we supposed to find a class boundary first? Then
No, you could do midpoints. It's a class midpoints, then class boundaries.
okay.
Yep.
But when we find the boundary, can we then the number we get when we subtract?
Well, I'm
0.
going to get there. I want to show something with class midpoints first. That's why. So we did the first class. The second class was from 70 to 109. You got to give me, no, it's not 88. It's going to be 89.5, right? So it's 70 plus 109 over 2, which is 89.5. Let's look at the third class. The third class was 110 to 149. So this will be 110 plus 149 over 2. Well, what would that be? 129.5. And you could develop a pattern, by the way, right? Look at your first class midpoint. It was 49.5. The next class midpoint was 89.5, and the third class midpoint was 129.5. What's the pattern? No, well, yeah, it ends with 0.5, but there's another pattern that you can recognize. What do we recognize between these three numbers? What is it going up by?
Add 40.
It's going up by 40s, right? And where do we get 40 from? The class width. So after you do a couple of the class midpoints, you should develop a pattern. Namely, you should see that the class midpoints are increasing by exactly whatever your class width is. So if we use that observation there, without doing much arithmetic, what would be the class midpoint for 150 to 189?
169.5.
That's right. Without doing the writing out, the actual math, just add 40 to the previous class midpoint. If you look at the next class, which was 190 to 229, what would that be? 209.5. The next class, which was 230 to 269, thank you. 249.5. And then lastly, for 270 to 309, that would be what? 289.5. All right, so after you do a few of them, all you got to do is just recognize, oh, wow, it's going up by the class width. Then you just take the class width and add it to get the rest of your class midpoints. Any questions? Yeah?
My professor mentioned something about how he would not have to guess the class to give it to them.
Say it again.
My professor, he mentioned how you always get the class that you don't.
Oh, the number of classes? That might be a different, I'm covering frequency distributions, but I don't know if he's implying that you have to create the frequency distribution from scratch. If you create it from scratch, the number of classes is given.
Oh.
Yes. Like, for example, if you have to fill in the frequency distribution table, like for instance, you got to talk about what your classes are, like their lower class and upper class limits for each of them, then you have to know what's the number of classes you want to use for your frequency distribution, whether it's 5, 6, 7, 8, whatever. That has to be given to you. Yes, O'Neill?
I said we had all the we finished, so we.
No, I'm not done yet. I never finished this problem. I only did the class midpoints. Now I got to go do the class boundaries. Okay. For your class boundaries, just like how you can, when you look at a specific class, you talk about the lower class limit and the upper class limit. There are what we call, there are what we call lower class boundaries and upper class boundaries. For the lower class boundaries, we need to subtract 0.5 to each of them. So for example, look at your first class. It had a lower class limit of 30. So if I subtract 0.5 from 30, what number do we get?
Um, 29.5.
That's right. It's going to be 29.5. Right. So yes, because by the way that these classes they only contain whole numbers. Right. These are all whole numbers. They're shown in the frequency distribution table. You just got to subtract 0.5. Yes. Well, if it was like another decimal, like it was like 30.4, yeah, 30.8, then you would have subtract 0.5. Or sorry, no, you don't subtract 0.5. I meant to say 0.05. So like this. I'll do this one on the board here. So if you had the 30.8, then that you have to subtract 0.05, not 0.5. You just got to keep adding a 0 in front of the 0.5. It's always one more decimal than the number of decimals that appears in the original data set. But if it's whole numbers, just simply subtract 0.5. So the first one is 29.5. What would be the next one? 69.5. The next one? Keep going. 149.5. 229.5. And the last one? No, there's one more for right now because we're doing lower class boundaries.
Oh yeah.
Only lower class for right now.
Okay,
269.5. Very good. All right, so those are your lower class boundaries. How about the upper class boundaries? Well, the lower class boundaries, it says that we have to subtract 0.5. On the other hand, for upper class boundaries, what do? Do you think we also subtract 0.5? Add, right? So we're going to add 0.5. Okay, so I'm going to add it and then we'll write out what the final answer is because you have to answer it in my lab in a specific way. So you're not wrong, by the way. Just wanted to clarify. I do them separately and then we put it all together. So let's look at the upper class boundary. The first one was the upper class limit was 69. So if I add 0.5, it will be what? 69.5. Continue. You can continue.
109.5.
109.5. 149.5. 189.5. 229.5. 269.5 and 309.5. There you go. So those are your your upper class boundaries. Now, in total, you write out your class boundaries in order, right? So on my lab, now I think there are some students that will be taking their my lab exam in person in the MS3 center. So on my lab, just be sure that when you write out your class boundaries, you write it in a specific order, right? So the class boundaries in order is 29.5, the 69.5, 109.5, basically everything from the lower class boundaries plus the one upper class boundary at the end. I see there was a question in the chat. Just give me 1 second to write this out, and then I'll clarify. All right, so I think somebody asked me in the chat, where did you get the 1.5 and the 0.5? I didn't get 1.5. You meant 0.5. Basically, the rule states that if you want your class boundaries, namely with your classes being whole numbers, then you, for the lower class boundaries, you subtract 0.5. On the other hand, for the upper class boundaries, you add 0.5. If I had a number like this, I'll write it in the chat so that way everybody can see it. If we have 30.8, I was mentioning this earlier. Notice that we have this value. Let's just say that it ends in 1 decimal place. Then for your class boundary, you would have had to subtract by 0.05, right? You always subtract by 1 more. You always put 1 more 0 in front of it. Basically, you subtract by 0.05 because you need to go by 1 more decimal place that appears than the original data set. Okay, so because your data set there, that value that I wrote in the chat is 30.8, then I would have had to subtract by 0.05. I had to put an extra 0 in front of that 5. Yeah? That's the rules. It's just that's the formulas. That's how I got it. Oh, so those were from that's from the table. Here's our table, right? The values were 30 to 69, all the way down to 270 to 309. We mentioned those were our lower class limits. Those were our upper class limits. So to get the lower class boundaries, just simply subtract 0.5 to each of them. For the upper class boundaries, add 0.5 because that's the rule.
Oh.
All right. Yes, Edwin?
For the class width, we say subtract any 2 consecutive.
That's right.
That can apply for both the lower and upper.
No, I mean, yeah, you can do it also for the upper if you like. 69 to 109, 109 to 149, still works. It's just more convenient just to say lower class limits. Yeah.
To find the boundary, we can also like add 70 plus 69 and like that too.
Say again. I'm doing what?
To find the class boundaries, can we also do 70 plus 69 and divide by 2?
I think you can. I never done it that way. From Pearson?
Yeah, it shows you that.
Oh. If Pearson shows it, then you could do it. If Pearson shows it. Basically, this session, I don't know how long it is because I can go on until I finish the whole review. As you guys can probably see, there's a lot of questions. So I'm trying my best ability to answer all your questions. So I don't know how long it can go. I'm willing to go as long as you guys want to go. So although I did only the first 5, that's great. I know it only took me 1 hour and 20 minutes, but I'll go as long as I can. I think another class comes in here until 6. So if I have to stay here till 6, I'll stay here to 6, no problem. Okay. I'm here to support you. I'm here to answer your questions.
And what about the thing for Saturday?
Same thing. I'll try my best to however to do it up to 1, from 10 to 1. I'll try to make it 3 hours. I'll probably give everybody like a few tokens, and every time you ask me a question, I'll probably take away a token. So that way I could save a little time. I'll try to do that one in 3 hours because we have a testing at 1. But if everything is covered for that testing session, then I could stay beyond 1. Okay. You continue? All right. Let's look at question 6. So here we're going to use the frequency distribution from problem 5 to construct your histogram. When you're constructing the histogram, your professor shows you how to do it in different ways, right? What we all know is that there's 2 things in common, all the professors, your axes, right? There's a pair of axes. There's one that goes up, and there's one that goes sorry, let me just fix that one. I don't like that line. Yeah, there's a y and x. You're right. Crap, let me get rid of it. Trying to get rid of that line. I need a bigger one. Okay, so we have a pair of axes. Yes, we call it y and x. But when you look at your frequency distribution table, right? What values? That's so no problem, Amy. When you look at your frequency distribution table, let's begin with the frequency. Does the frequency go on the vertical axis, the one that's going up, or the horizontal axis that's running to the right? Where do we put the frequency? The one that goes up, right? So for our frequency, so that way I don't have to go back and forth between the table, I can just tell you that our lowest frequency was the value 2, whereas the highest one was about approximately 23. So I'm going to go on for my frequency scale, I'll start with 0, but then I'll go all the way up to 24, but I'm going to go up by 4s. Okay, so I start with 0. I'll say this is 4, here's 8, here's 12, here's 16, here's 20, and then here's 24. Okay, then on the bottom, the horizontal scale, you put your classes. Now, usually you would try your best to fit that range, that, for example, the first class being 30 to 69, except what I show my students is that it's a little bit more convenient because of the way that the numbers are, they're somewhat large. It's just best to use the lower class limits. So the way I scale this is as follows. First, I put a breaker between 0 to 40. I call it, between 0 and 30. That's just bridging the little gap between those two values. And now I'm going to scale this by 40s because that was the class width. And when I scale it by 40s, those are exactly my lower class limits. So it's 30, 70, 110, 150, 190, then 230, and 270. 270 was the last lower class limits. Like I mentioned, if you had like for example, an Excel sheet, or you're doing this in R, whatever the case may be, I could have probably changed the font, changed my writing style to fit, for example, 30 to 69, or try to fit 70 to 109 in the next one. But no, just use your lower class limits just for the convenience of it. Now, for your histogram, you're drawing these bars. The bars are essentially the height of the frequency. So for the first class, the frequency was what value? Anybody remember? Well, let's just go back. The first class had a frequency of 2. So I'm going to make an eyeball approximation. If you look at my frequency, my scaling of it, I went by 4s. So technically speaking, where would 2 be located? Below 4, namely halfway mark of 0 and 4. So somewhere here. So that would be my first bar. Let's look at the next class. The next class was has a frequency of 6. So where would the 6 be located?
Between 70 and 100.
Yes, definitely is going to go there, but on the scaling of your frequency, on the other set of axes, the middle of 4 and 8. That's right. Now, one thing to note is that when you're drawing these, drawing a histogram, are there spaces between the bars? No, unless the frequency is 0. If the frequency is 0, then yes, you'll see a little gap. But we don't have to worry about it here because none of the classes have a frequency of 0. So this one will be 70 to 110. Okay, let's look at the next class. The next class has a frequency of 12. So just remember that when you're drawing these bars, there's no gaps. Okay, the next class has a frequency of 23. So I'm going to go up here somewhere. Technically, my drawing is going to get a little bad here. 6 is the next one. So we did that earlier. No, wait, did I made a mistake? Oh, the next one is 14. My apologies. So sorry that I'm going back and forth and I'm probably making some of you dizzy in the Zoom meeting. The next one was 6. And I think the last one was 3. Okay, so that's approximately what our histogram looks like. Now that you have your histogram drawn, the question now asks us, is it approximately normal, skewed, or skewed left or skewed right? What do you think? It's an approximately normal distribution. Now, what do we know about approximately normal distribution? What else does an approximately normal distribution look like? It looks like a bell. That's right. Approximately normal has this bell shape. I'm not going to draw the bell shape directly on top of my histogram because I'm not trying to make it look. I want to keep it as pretty as it is right now. But here's what your bell shape should look like. It starts low, it hits a peak, and then it decreases again. All right. Questions with problem 6? Okay.
If it was skewed left,
Oh, I do.
Go ahead.
If it were to be left or right, how would it look?
If it was skewed left, then if you think about the bell shape, then it's like taking that tail, taking the ending, this touch me. Oh, how did I do that? There we go. Sorry. I don't know what I did, but I thought it was touch me for a moment. Sorry about it. If it was left tail, skewed left, it's like pulling the left tail, per se, of the bell shape curve all the way to the left. So I'm going to draw this really small, but it looks something like this. That's what approximately a skewed left looks like. A skewed right, on the other hand, would have been taking the right tail, right? Think of the bell shape. Think of like as a cat, taking the tail of it, the cat, and you're pulling it all the way to the right. So that would have been skewed right. They're not the perfect images, but that's the idea. You're taking one of the tails of a bell and you're pulling it either to the left or to the right.
Professor, I have a question. I didn't really hear. So when you're doing like this hexagon, I'm sorry.
Histogram.
Sorry. When we doing the classes on the bottom, right? Are we only doing the lower classes?
Well, for convenience sake, yes, you can just use the lower class limits. That's fine.
Okay, thank you.
So if you had technology, like for example, if you're doing this on a computer software, then it's reasonable to fit the classes. But we're doing this by hand, so for convenience sake of your sketch, just use the lower class limits for each class. Any other questions? Okie dokes. Let's go to problem number 7 now. Problem number 7 states, consider the scatter plot shown to the right, and we're going to answer parts A, B, and C. Part A states, which of the following could be the value of R? So just please note that the first value is supposed to read negative 0.9525. The other one is negative 0.5725, then positive 0.5725, then lastly 0.9525. Part B then states, given that the regression line has a slope of 6.458 and a y-intercept of 51.202, find the slope-intercept equation of the regression line. And then part C, we're doing something a little arithmetic. So first of all, part A, we're talking about the value of R. R is what measures the strength of a linear correlation. Well, what do you think? Based on our scatter plot, do you think we have a strong or weak linear correlation? It looks like a very strong linear correlation. Why? Look at your points, yeah? Not because they're increasing. What else can we say? Yeah? You had your hand up. Well, it looks like it's going in a straight line. Namely, if I just drew a line, I don't know, I'm just drawing a random line. And it's not have to be this exact line. I'm just making one up. Let's say that line was something like, I don't know, let me just tilt this a bit. Let's say that this is our line, hypothetically speaking. Look at all those order pairs. Did all of them hit that line? No, but are they relatively close to that line?
Yes.
Yes, they are, right? So the way that we answer this question is that it's a strong linear correlation because all those points, all those order pairs falls very close to that line, right? Give me 1 second, O'Neill, right? So what we see here is a strong positive linear correlation. So the question now was to talk about what is the value of R. So looking at your 4 choices, what could be the value of R here? Or sorry, how about this? What 2 values do not make sense at all? Yeah, the negative ones do not make sense because if it was negative, the line would have been what? Decreasing. So you could get rid of those. So you just have 0.05, 0.5725 and then 0.9525. But which one do you think it is?
0.5.
Point what?
0.5725.
What were you gonna say? Unfortunately, it's gonna be the 0.9525. Why? Because the value of R, right? R can always be a value between -1 to +1.
So it's the closest to being one.
So it's closest to being 1. That's right. So in other words, when you look at the line segment that I drew, anything close to 0 is what we say weak to no correlation. Anything close to the -1, as you're getting close to -1, you can either get a strong or a perfect negative correlation. And if you're getting closer to the +1, then it's strong, strong or perfect. It's perfect if it's all the points lie directly on the line, by the way. Positive correlation. So because we said that it's strong positive linear correlation, then the best answer choice here would have been 0.9525. Sounds good? Okay, now part B states, given the regression line has a slope and a y-intercept, we have to write out the slope-intercept form of the equation. Well, part B is very simple. You just got to know what the equation is. In general, what does anybody know what's just the general equation of a line? Yeah, the general equation of a line is y equals mx plus b. However, in statistics, we use all these funny looking notations. So the notations that we use when we talk about regression line is instead of saying y, we say y hat is equal to b1 times x plus b naught, b0, right? So the b1 is essentially your m, right? So I'm writing this all out for you guys. M equals b1 is your slope, whereas b, which is equal to b naught, that's implying the y-intercept. In this problem, did it give us the slope and the intercept? Yes, it did. It gave us both of the values. The slope was 6.458, whereas the y-intercept was 51.202. So looking at our equation of the regression line, it's the one on the bottom, that notation. Looking at the slope and the y-intercept, just make a direct substitution. You're going to get y hat equals 6.458 x plus 51.202. And that's the solution to part B. Now we can do part C. When x is equal to 8, what do I do to solve for y? Yeah, you plug it into your equation. That's right. So when x is equal to 8, we can say that y hat is equal to 6.458 times 8 plus 51.202. And you do the arithmetic, right? So if you work out the final answer and then you round it, if necessary, to 3 decimal places, what would your final answer be? This you would have to use a calculator, most likely. Yep, so
102.866.
careful. The way that we say that last part is 102.866.
Oh, 866.
That's right. So y hat is 102.866. Any questions to problem 7? I'll put a little winky face on problem 7 for the departmental sample final. There's a problem like this, almost very similar to it. So this is an example that you might see again later on down the course. Yeah.
What if I'm not given the X?
And you're given y instead, then that's different. Then you would have to solve for x. If you were given y hat, then you would have to solve for x. I would have done an example, but I'm running out of room on this particular slide page. So I'm not.
Can I just see the formula?
No, it's the same thing. So I'll do a little simpler example because with these decimal numbers, it's a little harder. I'll do it on the board. Let's say if I had the equation y equals 4x plus, I'll make this 4x minus, I don't know, 8. And I want to find the value of x when y is equal to 12. Sounds good? Then by direct substitution, you're going to get 12 equals 4x minus 8. You would add 8 to both sides of the equation. This 8 is gone. You get 20 equals 4x. And then you divide 4 to both sides. So this will give you 5 equals x. So you're dealing with the same equation, but the arithmetic now is not that straightforward. Okay? Good? Everybody's good on this? I'm sorry about for those that were in the meeting. Somebody was asking me, what if you were given y and you had to solve for x? I use a more smaller example. I said if y is equal to 4x minus 8 and y was equal to 12, solve for x. If you actually work it out, you'll get 5. X is equal to 5. Can we move on? All right, so that's problem 7. Let's go to problem number 8. So problem 8 states, for the following set of sample data values, find the mean, median, mode, and mid-range, and if necessary, round your final answer to 1 decimal place. So before you answer, Edwin, just a quick heads up to everyone. If you are doing your exam, if your instructor is giving your exam on MyLab, or even if your professor is giving you your exam by hand, please pay attention to the rounding rules, right? The directions on rounding. If your professor wants you to round it to 1 decimal place whenever it's necessary, round it to 1 decimal place. Do not round it to 2, do not round it to 3. It states clearly round it to 1. For MyLab purposes, if you round it to, let's say, 2 decimal places, or you're not doing any rounding at all, the problem marked incorrectly and you get the whole thing wrong, okay? So just be mindful of the rounding rules. So just like how I have it here, usually on MyLab, the rounding stuff will come up in blue, in a blue font. Okay, so how do you find the mean for a data set? Excuse me. Yeah? That's right, we're gonna add up all the values. You take the sum of your data values and you divide it by the total number of data values. Now, because we're dealing with a sample, the data set is a sample data set, the mean, the notation for it is called what? Not n. No, the notation. What is the mean? We don't write the word mean. I mean, we can.
Oh, X bar? X
bar, that's right. That's what I was referring to. So our mean is, which is defined as x bar for samples, is equal to the sum of x divided by n, right? That basically means you take the sum of your data values and divide it by your total number of values. So can I get a volunteer? Can somebody first add up all those numbers? I'm not gonna write out all of it, but can somebody at least do it for me? If you take the sum of all the data values present in your data set, so let me know what you get. 615? Okay, now how many values are in our data set? 11. So you do 615 divided by 11. We round it to one decimal place. That's right. So if you enter 615 divided by 11 in your calculator, you're rounding this to approximately one decimal place. So this will give you 55.9. I'm not going to write out the full-blown decimal that's in your calculator. Say it again. What? Round what to 60?
56.
No, we're not rounding it to 56. You would have got the question wrong. You have to follow direction. It says round it to how many decimal places? 1. So what came after? What technically came after the 55 in your calculators? 909, right? So the 0 would have told the 9 to stay the same. So if you put 56, you're wrong. You got to put 55.9 because you got to follow. That's why I made that whole comment earlier. Follow the rounding rule. If it asks whole number, then yeah, it would have been 56. But it didn't ask us to do whole numbers. All right, so we got the mean. Let's get the median. Well, what is the definition of the median? The median is, what's another way of saying middle? Yeah, O'Neill? Say again? The 50%, basically halfway point, right? So median, it started off as the halfway point of a data set. The reason why O'Neill was saying 50%, because 50% of the values are going to be less than that value, 50% of the values are greater than it. It's almost essentially, we could say the middle value, but I just got to be careful because you have to look at your data set. When you look at your data set, how many values were there again? 11. N was equal to 11. Now 11 is what type of number, even or odd? An odd number. Because N is equal to an odd number, then the median is definitely going to be the middle value, as long as the data values are in order, which they are. But if there were an even number of data values, what do we know about even number of data values? What do we have to do if you had to find the median? You have to add 2 middle numbers and then divide by 2. So that's why I kind of stir away from saying middle. It's just because of the calculations that comes with it. So for this problem, since N equals 11 is odd, the median is going to be the middle value. So what is our median? That's right. If you work it out, you get 56. All right, we have the mean, we have the median. Let's get the mode. Yeah, the data value, the most. Yes.
Because there's more than one.
Mm-hmm. So the data value, so sometimes there could be more than one, that occurs most frequently. So what data value appears the most frequent? 58.
53.
Let's say if 53 appeared 3 times as well, then there were 2 modes. Let's say none of the numbers repeated more than once. There's no mode. That's right. So those are your options with modes. It could be no modes, 1 mode, or multiple modes, 2 or more. All right, and your mid-range. How do you compute mid-range? MR. Yeah, so I'll call it max and min. You add them up, and what do? Yeah, you say max plus min divided by 2. So what are my max and min values? O'Neill?
Your maximum value is 51.
Uh-huh. And the minimum?
42.
Okay, so we do 71 plus 42 divided by 2. If I enter this into a calculator, what do we get as a final answer? 56.5. So those are our four, our four answers to this problem. The mean was 55.9, the median was 56, the mode was 58, and the mid-range was 56.5. Any questions? Go ahead.
For the medium, so you put the number before the break.
When you're dealing with the median, you have to put the numbers in order. Any questions for me? You look like you want to ask another one.
I didn't get that. Like,
That's because you're doing it in your calculator. Unfortunately, you didn't put the numbers in correctly. If you're doing it in the calculator, you got to know how to put your numbers in correctly. I'm not showing you how to put the numbers in correctly in your calculators, unfortunately. I'm teaching you everything how to do it by hand. I'll show you how to solve all these problems by hand, where we use the calculator to do basic calculations. But if you want to go fancy, then you got to learn how to use that calculator on your own, or follow the instructions that your professor gives you. I think if everyone uses different calculators, right? Some has the graphing, some has a regular scientific calculator. So for me to go through all those steps or all those rules, I won't be able to. Not during the workshop, at least. If you come to the center, then maybe we can sit down and we look at it together. Okay. Oh, Lauren, yes. If the median is even, should we take the two middle values and divide by 2? Yes. Yes. You're welcome. I know what you meant. You're good. I have an example with that, but I'll save it for later. Okay, let's look at problem number 9 now. Problem number 9 states that 30 automobiles were tested for fuel efficiency in miles per gallon. The frequency distribution below was obtained, determine the mean, then round your final answer to 1 decimal place. So sorry, I forgot to hold that in blue. But then we're going to compare that computed mean to the actual mean of 17.8. Okay, so this was a problem that you probably encountered on MyLab. And there's a way to compute the mean for a group frequency distribution. So here's our formula. I'll write it on the top. We say that X bar is equal to the sum of F. Anybody remember what F stands for? Frequency. I didn't write this notation previously when I talked about this phrase, but what does the XM stand for?
Midpoint.
The class midpoints. That's right. So it's the sum of the frequency times the class midpoint for every single class divided by the sum of your frequency. So that's our formula. Now, when you're doing it using a table, right? When you're using a table method, informally, now this is not formal, it's just an informal way when you're using the table, what you're going to see is that we're eventually going to take the sum of column 4. Basically, this is how I'll explain it to my grandma. You take the sum of column 4, and then you divide it by the sum of column 2. So what I need to do is extend my table, right? My table already has 2 columns. The first column is my class. The second column is the frequency. I need 2 columns, 2 more rather. The 2 more columns that I need are going to be the midpoints, and then, the midpoints, which are XM, and then our frequency times the midpoint. Okay, so what do you think? We showed how to compute midpoints earlier. What do you think would be the midpoint for the first class, 7 to 11? 9. We took 7 plus 11, and we divided by 2.
9.
Right?
Gonna be 9.
That's right. So 7 plus 9, then divide by 2. Sorry, 7 plus 11. My bad. This is going to equal to 9. Okay, And then to fill out the last entry box there, you take the frequency times the midpoint for that row. So what's 3 times 9? 27. Okay, and now we're gonna repeat this process. The next class is gonna have a midpoint of what? 14, right? You take 12 plus 16, divide that by 2, you're gonna get 14. And then you do 5 times 14. By the way, for those that are here, is it okay that I close the door? They always do this to you at this time. Last semester when I taught Math 108, trigonometry, I understand we have to make the college clean, keep it clean, but not during this time of the day. At least wait until the 6 to 7:40 class is over. It drives me insane. What's 5 times 14? 70. Okay, let's look at the next class. What would be your midpoint? 19. So I'm just gonna write out these numbers now. So we get 19. Then we're gonna do 15 times 19. That's gonna be what? 285. And then for your next class? No, your midpoint. Oh yeah, wait, no, it's not 35. 24. Ooh, careful. That was your phone? No, my phone, I used to like the iPhone 5 because of that. The iPhone 5 used to drop so many times with that Raphael, and it never cracked. Screen never cracked. 12? Yeah, I got the 12 as well. It's somewhere here in this room. Okay. So we take 5 times 24. What would that be? 120. And then for your last class, 29. And then we do 2 times 29. 58. So informally, what does the formula say? What do you tell grandma to do? That's right. You tell grandma to take the sum of column 4, and then you divide by the sum of column 2. So I'm just going to create an extra box for my sums. So what is the sum of, let's say, column 4, f times xm? That one's just going to take us a little longer to do, but that's okay. No, that would be column 2. Column 2 is going to be 30. I asked for 4. Column 4.
506. I'm 560.
560. That's okay. We got 560 over 30. So what we're going to say is that x bar, now look at the formula above, is the column 4 divided by column 2. So if you take 560 divided by 30, you got to make sure that you round this to 1 decimal place. So if we do the calculations, 560 over 30 divided by 30, then round to 1 decimal place, what is our final answer? Try again. What came after the decimal point? What were the first 2 decimal numbers after the 18?
18.66.
Wait, what came after the 6? 18 point what?
18.66.
The 6 is repeating.
6.
Okay, so what does the 6 in the second decimal place tell the 6 to do in the first decimal place? Round up. So what comes after 6? 7. So why are you guys saying 18.6? It should be 18.7. Right. So the units should have been miles per gallon. So I'm just writing it out. Okay. So X bar is 18.7.
560 added 27, 70, 25.
That's right. That's what it means to take the sum of column 4.
The sum of column.
Yep. Okay. Now let's just do the other part. We got the answer that we wanted. This is something that you'll see on MyLab. So in short, you're computing the relative size or percentage between the computed value and the actual value, right? So the rule of thumb here is that if it's less than or equal to, don't quote me on this, I think it should say less than or equal to 5%, or if it's approximately close to 5%, then we know that the computed mean is relatively close or reasonably close to our actual mean, right? So here's how you compute this, or how you check this. Take the computed mean, which is 18.7, and then you subtract it from the given mean. What was the given mean? The one where it's actual. 17.8. So you take the actual mean, and then you divide it by that actual mean. To really understand why I'm doing this, you would need a course in quantitative reasoning, Math 126, but that can take a whole hour and 40 minutes to explain, so I'm not going to go that in depth. But long story short, we're computing a relative change, a percent change. So you take the 18.7 minus 17.8, what would that be? You don't have, you have a phone? At least you use your phone, it's calculated for now. So you got 0.9 over 17.8. Now, I want you, when you compute this, you can round it to 2 decimals, that's fine.
Decimals. It's gonna be 0.005.
Yeah, 0.05. What is 0.05 as a percentage, by the way?
5%.
5%. This is going to be approximately 5%. So is 5% close enough to 5%? Yes, it is. Right. So with the rule of thumb here, because 5% is less than or equal to itself, then we can say that the computed mean of 18.7 is reasonably close to the actual mean. And you're done. The actual mean, by the way, was 17.8. By the way, the way that they got the 17.8 is when they looked at the specific data values for each class, right? When you're getting a frequency distribution, when you're given a frequency distribution table, the way that we computed the mean was assuming that all the data values are essentially the class midpoint, but that's not necessarily true. In this case, it's definitely not true. If it was, then we would have got back 17.8. Questions to problem 9? Yeah, Edwin? It was given in the problem, actual mean of 17.8. That's right. Question there?
Are those numbers from that?
What numbers from what formula?
The numbers the second.
Oh, in the little box?
No, not here. That.
Here?
Yeah.
How did I get these numbers?
Yeah.
This ones? You gotta tell me guys the point. Or tell me the midpoints or the last ones. The midpoints, I use the formula.
Yeah.
7 plus 11 divided by 2. I wrote that there. 12 plus 16 divided by 2. I stopped writing it out because we followed the pattern. And you can also take the class width. What is your class width? Class width? 5. So after you found out that it was going up by 5, just add 5. You're welcome. There's different ways to do it. You can just do it the first 2 way using the formula, and then just see that the class width was 5 and add 5. That's something I mentioned way back when I did problem 5. It sounded like we did that like 3 hours ago. All right. Any other questions? We're good? Okay. Now we're gonna go to problem 10. So like I said, most of these things that we're doing here, you could probably do them in your calculators, but because everyone has different calculators, I'm showing you the formulas and the tables that we use to do them by hand, okay? So here we're finding the range, sample standard deviation, and sample variance for the given data values below, and if necessary, round all final answers to the nearest 100th place. When it says 100th place, how many decimal places are that? 2 decimals. So keep in mind, 100th means that we're rounding it to 2 decimals. Okay, so let's go about this. How do we compute the range? I think the range is the simplest way, or it is the simplest way to compute variation in a data set. Maximum minus the minimum. Fortunately for us, I think we should be able to identify the max and mins here. They're going to be what values? 23 and 8. So you do 23 minus 8, you're going to get 15. So that's it. That's it for the range. We're done. Now we have to go into sample variance and sample standard deviation. So I'm going to write out their formulas for both, and then we're going to do a table for them. So we have sample standard deviation, sample variance, I meant to say first, and then sample standard deviation. For your sample variance, we denote it as S squared. And we say that S squared is equal to the sum of X minus the mean squared, all divided by N minus 1. How do I explain this to my grandma? Well, when I use a table, I'm going to say the sum of column 3 divided by N minus 1. For sample standard deviation, we say that S is equal to the square root of S squared, which means that you're taking the square root of that entire formula. You take the square root of X minus X bar squared over N minus 1. When we're doing this by hand, just keep in mind, we need to create a table. Your table consists of 3 columns. In one of your columns, just like the formula mentioned, you have to take the difference between each data value from the mean, right? So first, in order to do both sample variation or sample standard deviation, first find the mean. Your mean is X bar. So to get X bar, this is going to be the sum of your data values divided by the total number of data values. So if I take 8 plus 10 plus 11 plus 12 plus 14 plus 23, what would all those numbers add up to be? $78. So we take 78 divided by the total number of data values, which is 6. Okay, so you do 78 over 6. If we do 78 over 6, that's going to equal to what number? 13. So you got your mean. Good. Now we're going to, I'm just going to slide this down. Now we're going to create and complete the following table. So the first column should be all your data values, which are the numbers 8, 10, 11, 12, 14, and 23. Your second column is where you take each data value and subtract it from the mean. So what's 8 minus 13? Negative 5. 10 minus 13? Negative 3. 11 minus 13? Negative 2. 12 minus 13? Negative 1. 14 minus 13? 1. 23 minus 13? 10. 23 minus 13 is 10. Now, in the third column, you're going to take each data, the values that you got from column 2 and raise it to the second power. Now, be mindful that when you're raising or when you're taking a negative number squared, the result is always going to be what? A negative number squared is always positive. So if I take negative 5 squared, that's like saying I'm taking 5 squared. So what's negative 5 squared? 25. Oops, my bad. You get 25. What's negative 3 squared? 9. Negative 2 squared? 4. Negative 1 squared? 1. 1 squared? 1. 10 squared? 100. Okay, so now to find the variance, we got to take the sum of column 4 and divide it by column 3 and divide it by n minus 1, right? In quotes, sum of column 3 divided by n minus 1. So if I do take this sum of column 3, what do we get?
$140.
140. So we say s squared is equal to 140 divided by n minus 1. What was the value of n again? What does n tell us?
6.
N was 6, the number of data values. So 6 minus 1 is 5. So in your calculator, you should do 140 divided by 5. What's 140 divided by 5? 28.
28.
All right, so I'm just going to write this out on the side here. Sample variance, which is denoted as s squared, is equal to 28. Okay, now finally, we do the standard deviation. For the standard deviation, you say that s is equal to the square root of your variance. So we got to take the square root of 28. Because 28 is not a perfect square number, you're going to get a decimal number. Be mindful that you have to round this decimal to 3 decimal places. So what is the square root of 28?
Wait, oh, there's 200 space in here.
Oh, we're doing it to the hundreds, 2 decimal place. I'm sorry. 5.29. Okay, so those are our answers. Sample variance was 28. Sample standard deviation, S, is 5.29. The range that we did earlier was 15. Any questions? Yeah?
Why do you put 6 minus 1?
That's part of the formula. The formula says that when you deal with a sample, not population, sample, you do n minus 1. The number of data values in the data set subtracted by 1. Any other questions? I saw a second hand up. Any questions in the chat? Okie dokes. Can we move on? All right, so we're halfway through. Now we're up to problem 11. Problem 11 states that we have to find the 5-number summary, then construct a box plot for the number of tornadoes recorded in each month in 2005. So what is the 5-number summary? What does the 5-number summary consist of? There's there's no Q4, Q. What's Q4, Q5?
Page, what, isn't it page 25?
Max and mins, those are the obvious ones. The five number summary consists of the smallest value, that's the min. It's okay. Q1, which is your lower quartile. Q2, which is the middle quartile. Q3, which is the upper quartile, and then the max, the largest value in your data set. So here's my guidelines that I recommend. Now, again, you can easily do this in a calculator, and you can probably do this in like a minute, less than a minute, probably 30 seconds, depending on the data set. But again, I'm showing you everything by hand, all right? Everything is done by hand. So the guidelines here is the following. First, if necessary, put the values in order. Usually when I say in order, I mean low to high. Is the data values in our data set in order? Nope, we have to do it manually then. Okay, so the second step says to determine mins and max. Part 3, or step 3, is to find Q2. Now, Q2 again is called what quartile? What's the name of it? What type of quartile is this? Lower, middle, upper? Middle. The middle quartile is like saying P50, percentile 50, or the halfway point of a data set. Now, we've heard about halfway point of a data set before. That was used to define what word? When we talk about the halfway point, the 50% mark of a data set. No, we saw it earlier. The median. It's referring to the median. So if you want to find Q2, you would have to find the median of the entire data set. Okay. Now, if you want to find Q1 and then Q3, you'll either have to do medians now of a lower half and upper half. O'Neill, hold off on your question. I want to try to get through the whole problem first. Okay, so we're gonna have to do these 5 steps, unfortunately. The first step we can't skip because we have to put the data values in order. So if I do put these values in order, what goes first? 10. What goes after the 10? 18. What comes after 18? 26. After the 26? 33. 62. 123. 123 again because it appeared twice. All right, so if you want, I can just cross these out, the ones that we did so far. So because 123 appeared twice, you have to list it twice. Then 132, 133, 138, 150, 316. Okay, crossed everything else. We got it. All right, so look at your data set, by the way. How many data values do we have? 12. I'll let n be the number of data values. N is equal to 12. And what do we know about 12? What type of number is that? 12 is even. 12 is an even number. Okay, so that will help me when I got to find Q2. So first, let's talk about the mins and max. What is your minimum value? 10, right? So I'll draw arrows at these values. So we have that the min is 10, the max is, that's right, 316. Now, because n is equal to 12 and we have an even number, then to get Q2, it would have to be the 2 middle values in this data set divided by 2. Right, so we get Q2, it's equal to the 2 middle values of data set, the whole thing, divided by 2. So what are your 2 middle values? Yeah, O'Neill?
I see the middle value is 123.
Yeah, both of them are they're going to be 123s. That's right. So if you take the sum of 123s and divide it by 2, you're going to get what? You're going to get back 123. That's right. So here's how I'm going to show this on my data set there. Remember, a median is a halfway point. So in order for me to show that 123 is the halfway point of the data set, then I can separate it into a lower half and an upper half. Right? Separate it into two parts. Just draw a line between those two middle values. So we have that Q2 is located here. 123. So above, this is your lower half. Anything to the left of our vertical bar that we draw. The upper half consists of anything after the 123 there. Okay, so let's look at Q1 now. To get Q1, we take the two. Well, how many values are in the lower half? There were 6 values there. So Q1, to get it, you have to take the median of the two middle values divided by 2. So those two middle values are what numbers? 26 and 33 divided by 2. So what's 26 plus 33? 59. 59 divided by 2? 29.5. So technically speaking, between that 26 to 33 there is your Q1, which is 29.5. And lastly, for Q3, how many data values were in your upper half? It was also 6. It starts with the 21, 23 that comes after the red bar, and it goes all the way up to 316. So what are your two middle values there? 133 and 138 divided by 2. So what's 133 plus 138? Mm-hmm. 271 divided by 2 is
135.5.
mm-hmm. So it'll be located here. That will be it. So the 5-number summary, oh, I ran out of room. The 5-number summary is what I have written out. So it would have been, the final answers are 10, 29.5, 123, 133, 135.5, and 316. That's your 5-number summary. Thank you, Raphael. Raphael, would you mind sharing the link to our website? Just to have it on the chat. Okay, now we just got to do the box plot. Look at your data values, by the way. What was the smallest data value there? 10. The largest? 316. So it might be reasonable that when we look at the horizontal line for the scaling purposes, we're going to go by 30s. Right, so we're going to do the box plot. So I'll do it down here. Oh, I might need a little bit more room than that. So let's say down here. So here's 0. That's our starting point. Here's 30. Here's 60. Here's 90. Here's 120, 150, 180, 190. 210 rather, 210, 240, 270, 300, and then 330. Okay, what is your so when you're doing the 5-number summary, thanks, Raf. The smallest value, your 5-number summary, you plot them. So the number 10, just using an eyeball approximation, should be close to the 0. The Q1, which is 29.5, 125 should be close to 30. 123 is close to the 120, to the right of the 120. 135 is somewhat smack in the middle. And then lastly, 316, which is somewhat halfway at 300 and 316. So those are your 5 number summary plotted. To do the box plot, you draw a horizontal line that extends from the minimum to the maximum. Then you draw a box that goes from Q1 to Q3. So I was drawing the bars here. And then you draw a vertical line that goes through Q2. So technically speaking, this is what your box plot looks like. Is there any sort of what does this distribution look like, by the way? Does it look normal? Does it look skewed? Which one is it? Normal or skewed? This looks like the wrong link. Oops, I don't know what the hell's going on. Oh, sorry.
Straight to the left.
Oh, no, we're good. Yeah, so does this look anything skewed or not? Well, sorry, what type of skewness? We did mention skewed.
Straight to the left.
Not quite. It has to be skewed right. It should be skewed right. Because if you think about it, look at your 2 tails. Which one is longer? The left tail or the right tail? The right tail. So it has to be skewed right. Technically speaking, look at the rest of the values compared to 316. Is 316 relatively close to the other set of values here? No, 316 is what we call an outlier. And an outlier can definitely affect your calculations and even the shape of your distribution. If I were to remove 316, I'm not going to do it now, but if I were to remove 316, then our data set would have been completely different. We would have had different values for the 5 number summary. All right. Any questions to problem number 11? Okay.
How did you know that you had to divide the line by 30s? Like,
oh, I just did a rough scaling. Yes, we're gonna keep track of attendance. That's right. Whoever's in the Zoom meeting, the attendance are there automatically. Let me just check something real quick. You have classes here? This is the statistics workshop. You gotta go upstairs for that. Because you're not in statistics, you're in 171. You gotta go upstairs. That's 233A. Okay, somebody else asked me a question here? All right. Okay. Yeah, I know. No, well, the thing is that I try my best to go through them. You know, yeah, trying to. I could rush through it.
No, don't rush. This is very thorough. That's
Yeah.
the way
No, I mean, no. I could rush through the whole thing. It's just that I don't want to. Whenever I do a review, I never feel comfort with rushing through it. That's why. But sometimes if I want to do a problem and I have a certain way of doing it, and you have a question, sometimes I kindly ask just wait until the end to like do the problem, because then it throws off my thought process a little bit of whatever I was thinking about saying. Okay. So yeah. Oh, somebody was asking about the scaling stuff. Yeah, it's just based off the numbers. I was scaling it by 30s. It was just an eyeball approximation. I saw my lowest number was 10, highest was 316, so I went up by 30s. Okay. See, like that person knocked the door. He was in math 171, so he needs assistance. Got to go upstairs for that. Unfortunately, I can't help him. I gotta go up to problem 20.
20?
That's right.
I gotta go. Talk to my 5 minutes.
Already.
I'll be.
Oh, wait, before you go, let me just hand out an attendance book real quick. Shit. Did this earlier.
I'll probably be.
No, that's not my attendance book, sir. Gotta be patient. Sign your name, please. You could actually pass that around. You could pass it to the next person. Okay, so let's look at problem 12. Problem number 12 states that adult males have foot lengths of width have foot lengths with a mean of 27.32 centimeters. The of shouldn't have been there. And a standard deviation of 1.29 centimeters. Is the adult male foot length 30 centimeters significantly low, high, or neither? So there's a way to answer this question. There's a method, actually. That's what I wanted to say. There's a method to answering it. Anybody know what's the name of the method? What is the method used to solve this problem?
Something like 2 plus.
You're getting there.
Yeah.
Something that involves a 2 and there's a plus, yes. But what type of measurements were given to us here? Or not measurements rather, but what type of a standard deviation and a mean? That's right. What we're going to be using is something called the range rule of thumb. Let me just draw the picture and I'll show you how the calculations are done. The range rule of thumb separates significant values from not significant values. So at the center of our distribution, we have our mean. So I'm going to use the notation as if we're dealing with a population. So mu looks like a U. I'm drawing a U. That's our mean for a population. And little sigma, which looks like a little cherry, is our standard deviation for the population. So there are 2 limit values. There's 2 values that separate significant versus not significant. So the way that we get those 2 values is by first taking the mean minus 2 times the standard deviation. And then we take the mean again, and we add 2 times the standard deviation. Again, that little symbol that I'm drawing that looks like a cherry is the standard deviation for the population. The U is the mean for a population. So the values that are not significant or considered not significant are anything inside of the range in between the 2 values. Anything outside, we call them extreme values or even significant, right? Significant, unusual, extreme, they all have the same meaning. So I don't know which ones your professor uses. So here we say it's significantly high versus significantly low. Okay, so to answer this question, figure out the 2 values, right? I'm going to circle them. Figure out these values that separates the significance versus the not significance. And then you get to answer the follow-up question. So for the first one, you take the given mean, which we know what it is, by the way, minus 2 times the standard deviation. The mean is equal to what value? 27.32 minus 2 times our standard deviation, which is 1.29. To get the other value, you take the mean plus 2 times the standard deviation, which is 27.32 plus 2 times 1.29. So what are these values that you're going to get? Finish, thanks. Mm-hmm. 24.74. And the other one? 29.9. So approximately, by the way, what the range rule of thumb tells us, approximately 95% of the values are between 24.74 to 29.9. Okay, now we answer the follow-up question. We were given a data value of 30 centimeters. Compare 30 centimeters to the range that we formulated or created. Is 30 inside or outside of that range? Well, look at your number line, right? Let's say if this value is 24.74 and this value is 29.9. Where is 30 located? Inside or outside? Outside. And if it's located outside, it's good. In this case, it's greater than the mean plus 2 times the standard deviation. Is going to be significantly high, right? Data value of 30 centimeters is, sorry, significantly high. Because technically speaking, it's located outside of your range. And somewhere there, roughly speaking. Any questions? It gets better, somewhat. But that's it. That's the answer to problem 12. There's the range rule of thumb, and there's another rule that follows after it. By the way, one rule that I'm not going to be covering is Chevy's theorem. Instead, I'm doing the empirical rule, which we're going to see in problem 13. Is it okay if we move on? All right. So problem number 13 states that suppose that a daycare cost orderly distributed. We already know what that word means. What type of shape is it going to be? A bell with a mean of 10,000 a year and a standard deviation of 2,100. So for this problem, we're going to sketch a bell, but we're going to apply the empirical rule. The empirical rule only works, or for this case, it works when we're dealing with a normal distribution. There are 3 important numbers when you're dealing with the empirical rule. What are those 3 numbers or those 3 percentages? 68 is the first one. The next one? 95 and no, it's 68, 95, and there's one last one. 99.7. He was close. All right. So the way that the empirical rule works, let me just draw a bell for us. Now, that's not the best of bell, but we're going to live with it. It's fine with me. So here's how it goes. At the peak or the center of your distribution, which wasn't even here, it's okay. You have your mean. Hello. So what is the mean here in this problem? 10,000. Now, the bars or the dashed lines, rather, those dashed vertical lines that I'm drawing, they're going to indicate when you're 1, 2, or 3 standard deviations below the mean, right? So let's say I drew another one. Let's say somewhere here. Not the best, obviously, but if you take the standard deviation, the mean minus the standard deviation, that implies that you're 1 standard deviation below the mean. So if the mean is 10,000 and the standard deviation is equal to 2,100, then what would that value be? Mean minus standard deviation. The mean is 10,000, standard deviation is 2,100. So if I take mean minus standard deviation, what will be that value? 79. Yes, 7,900. Okay. On the other hand, if I were to add the mean to the standard deviation, mean plus standard deviation, 12,100. Okay, so this would have implied that 68% of your values are in this range. Okay, now let's do for the 2 standard deviations. If we're 2 standard deviations, let's say somewhere here, just so that way I could write this out, below or above the mean. Well, if I take the mean minus 2 times the standard deviation, what would that value be? Say again. Take the mean. Yes, 5,800. On the other hand, if I were to add 2 times the standard deviation to the mean, what would that be? Very good. And now, let's say if I do for the 3 standard deviations. What would the values be? $3,700 and 16,300. Okay, so just to recap here, if you're within the 2 standard deviations now of the mean, then that would be the 95% from the empirical rule. And now, lastly, if you're 3 standard deviations, you get the final percentage. I'll put the bar here. Okay, so let's answer this question now. Look at your ranges, 3,700 to 16,300. How many standard deviations within the mean are you? 1, 2, or 3? Try again. 3, right? From 3,700 to 16,300, that is basically within 3 standard deviations. And now you get to answer this question based on your chart, right? If you're within, that's right. So within 3, I'm gonna abbreviate this, standard deviations, this implies that the percentage by the empirical rule must be 99.7. On the other hand, if you have 7,900 to 12,100, how many standard deviations are you within the mean? 1. You're within 1 standard deviation, so that would be 68%, right? When you're using the empirical rule, there's only 3 answers, 68, 95, or 99.7. The way that you get them is this picture. Draw the bell shape. Okay? So empirical rule, there's only legit 3 answers you can get based on the way this question is worded. Yeah? You can ask your question. Somebody.
Okay, excuse me. What's the number 5,800 and 14,200? I didn't see the number.
Those are 12,100, 14,200, and 16,300. The way that you hold on, give me 1 second. The way that you compute them is if you look at the formula that's above it, you would have to take the mean plus 1 standard deviation, then the mean plus 2 standard deviation, then mean plus 3 standard deviation.
How you get a 5,800?
Well, you have to now do the opposite of adding. You subtract, because those values, if you look at their locations, they are less than or below the mean. So, for example, take the mean, which was 10,000, minus 2 times 2,100, and that gives you 5,800. If you want the 7,900, then just do simply mean minus standard deviation, and then the last one, mean minus 3 standard deviations. Okay?
Okay, thank you.
You're welcome. Anybody else? All right, so problem 13 is the empirical rule. Please make sure that you read the way that the question is worded. If it state, I think, by the way, I should mention this. I think if you do have your exam on MyLab, it will state to use the empirical rule. On an exam, I think by paper, I think they would also state to use the empirical rule. Okay, that's problem 13. Let's look at problem number 14 now. Problem number 14 states that we're at a departmental store and we're doing some shopping. It has a daily mean sales of $34,291.67. Basically, I want to give you a real life application to this one rather than textbooks. The standard deviation is approximately 3,000. On Wednesday, the store sold $30,641.72 cents worth of goods. On Saturday, the store sold $41,416.23. Find the z-scores for both Wednesday and Saturday. Was Wednesday a significantly good day? Was Saturday a significantly good day? Okay, so what is the formula for finding z-scores? We say z is equal to what? Have you guys covered z-scores? Okay. Just checking, because now this is the part where I don't know where you guys, I know you guys did up to standard deviation and 5-number summary, but I don't know if you guys did the z-scores yet. What is the formula we use to get a z-score?
Z-score is x subtract mean divide the deviation.
That's right, standard deviation. So just remember x is our data value. So that's our formula. So we're gonna have to apply this formula twice. Just know that there's a rounding rule with this formula. Z-scores are always represented or rounded to 2 decimals if needed, okay? So we're gonna compute, I'll call it Z Wednesday or Z Wed. That stands for Z Wednesday. And then we're gonna do Z of Saturday, SAT. Okay, so just insert your numbers, your values into the formula for both Wednesday and Saturday. For Wednesday, what was the sales again? $30,641.72. So we take that value, subtract it from the mean, which was 34,291.67 cents, divided by your standard deviation of 3,000. When you guys compute this, do the subtraction first in your calculators and then divide by 3,000. When you do, make sure you round your final answer to 2 decimal places. Well, you got to round it to 2 decimals. That's right, -1.22. All right, we're going to repeat this process now for Saturday. We're going to take our sales, which was $41,416.23 minus the mean, $34,291.67, divided by 3,000. Be sure that when you do your calculations, again, round it to 2 decimal places. Okay, so we have to answer both the follow-up questions. Z Wednesday and Z Saturday are great. We just got to figure out if there are significantly good days. So Z Wednesday, was it Wednesday a significantly good day for this departmental store? No. Can we say that it was a bad day, a significantly bad day? Unfortunately, no. We can't say that either. The rule of thumb for z-scores is that it's not significant when z is between -2 and 2. That's, remember, z tells you the number of standard deviations you're away from the mean. So if you're within, this basically goes back to the idea of the range rule of thumb. if you're within -2 to +2, then that's okay. Then it's not a significant value at all, right? So Z Wednesday, Z score for Wednesday is neither significantly good nor bad, significantly bad. And the reason why is because that value, -1.22, is between -2 to +2, right? Because Z equals -1.22 is between Z equals -2 to Z equals +2. All right. Was Saturday a significantly good day?
Yes.
Yes. Why can we say that it was a significantly good day?
Because it's a positive number and it's higher than
Not higher than 1, but higher than 2. All right. So Saturday was significantly good day because Z equals 2.37 is greater than Z equals 2. Now, let's say that if I had -2.5, like so let's say Monday, we did a Monday Z score, and let's say that Z Monday comes out to be -2.5. Would it be significant or not significant? -2.5. Yeah, Lauren, you're right. -2.5 would be significantly. Yep. Because it's less than, yeah, significantly bad because it would have been less than -2. Right? Think of this range. Right? The range goes from -2 to +2. If you want to plot -2.5, that's here somewhere. Right? -1.2 is like, I don't know, right here somewhere. And then the other one was 2.37. So let's say somewhere here. Yeah, just think about -2 to 2. If because it all goes back to that range rule of thumb problem. Because by the definition of a Z-score, it tells you how many standard deviations you're away from the mean, whether that's above or below. The Z-score formula? It does. But they might write it out using population notation or the means notation. I'm just writing it out in plain English because the formula is still the same. Data value minus the mean over standard deviation. Questions? All right, the next problems 15 through 20, we're gonna look at probability. I think problem 15 is actually the most easiest problem on my review. For students that are in my class, just to give you a heads up, this problem is definitely gonna see it on the exam. This is like my gimme question. Which of the following values cannot be probabilities? What do we know about the probability of some event A? It's always between 0 and 1, right? So if A is some event, I meant to say if A is some, not a sum. If A is some event, then the probability of A denoted as P of A, right? It's basically, we write the letter P first, then in parentheses, whatever your event, namely A is between 0 to 1. And we include the 0 and 1, right? So as an inequality, it looks like this. 0 is less than or equal to the probability of A, less than or equal to 1. So any value that's basically negative or any value that's greater than 1, they cannot be probabilities. So which values cannot be probabilities? Can I get one value? That's right, 1.73. What else?
8 divided 3.
Yeah, definitely 8 divided by 3 because those are values greater than 1. Is there any other value that's greater than 1?
No.
Yes, there is.
Three. What's that's called the
Careful.
three
Square root of 3.
square.
Yes.
Yeah.
The square root of 3. That's definitely greater than 1, because if you enter that in the calculator, it should be like 1 and change. Those are all values that we cannot be probabilities. I heard one more answer, which was actually wrong. That answer that you guys said was 1.29%. You see, there I got everybody. I got you. That's where I could, throw my strike free, my curveball, and get you out of the game. You see, 1.29%. You can actually write this as a decimal number by simply dividing the percent by 100, because that's what percent means. Means per means divide, cent means 100. So if you take your percent value 1.29 divided by 100, what is this as a decimal? Yeah, 0.0129. And if you look at that value, is it greater than 1? No, I mean, is that no? It's less than 1. So this is actually it's close to 0, but this is actually a probability value. So the only values that are not probabilities are negative 0.06, the square root of 3, 8 over 3, and 1.73. And we're done. Here's one more example, just because I did percentages. If I had 300%, right? If you use my idea there by dividing the percent value by 100, what's 300 over 100? 3. Is 3 a probability? No, that would have been not a probability. But the 1.29, I got everybody. I felt like Vince McMahon. Felt like Vince McMahon on that one. I forgot the episode it was. Huh? Problem 14? Sure, go ahead. All right. We're all good on problem 15? Okay, now we're going to problem 16. Problem 16 is very wordy, but it's actually very easy. It's based on a new generation of Staines survey. Approximately 130 out of 1,000 adults know that the care instruction symbol, in math we call it delta, that triangle, we call it delta, on clothing means that any bleach can be used. I didn't know that. Based on this result, we can say that the probability of A is equal to 0.13. The way that they got the 0.13, by the way, is that they took the 130 and they divided by 1,000. Where A denotes the event of selecting an adult that knows that the care instruction symbol, delta, on clothing means that any bleach can be used. What does P probability of A bar denotes, and what is its value? So what is the difference between these two notations, probability of A and probability of A bar? Don't say that the obvious is one has a bar, the other one doesn't. They have a significant meaning. You have to know the notation. What do we call these events, A and A bar? Thank you, Amy. Thank you for mentioning. Say again. Complement? That's right. They're complementary events. What's another way of I can't spell right now. Complements. Whatever, I can't spell it right now. But complementary events. What's another way of when we think about complementary events? Well, it means
1 minus PA equal a PA. This what?
Yes, it means probability of A bar. That's right.
Yeah,
that's the
PA
formula.
bar.
That's the easy part. The formula is the easy part. Understanding the formula or understanding these notations is more important, because we're going to use it again later on to wrap up tonight's review. But complementary events means that, or A bar, let's start with that. A bar means not A. That's it. It's like saying the opposite. Like, let's say if I said that today is a sunny day. Today is a sunny day. What would be the complement of saying sunny day? What's one possibility? It's a rainy day, or it's a gloomy day, cloudy, snowy day. All right. So A bar just means not A. Well, the problem tells us what probability, what the P of A stands for. We just got to talk about what does the P of A bar means in plain English, and then compute its actual values in the formula that Ms. Tamero mentioned. So the probability of A bar denotes the event of selecting someone. Basically, I'm going to rewrite everything of event A here, except there's one keyword that I'm going to use now. The one keyword that I'm going to insert is the word not. So denotes the event of selecting someone or selecting an adult that does not, shit, I'm writing really sloppy, does not know the instructions or the care instructions symbol, which is delta on clothing, means that bleach can be used. All right, so whatever A was, A bar means not A. All right, so the way that we compute not A, we say that P of A bar is equal to 1 minus the probability of A. And the probability of A, we already got that value. It was given. It was what? Probability of A, 0.13. So you take 1 minus 0.13, and that will be your final answer. You get? Point. What's 1 minus 0.13? 0.87. There you go. Done. Any questions? Can we continue? You want to snap a picture? You got it? Okay, so problem 17. So for problem 17, 18, and 19, we're going to learn how to compute probabilities of a two-way table. Usually when you're dealing with a two-way table, there's basically two variables. For example, when you talk about cars, you can separate them based on if they're foreign or domestic. And then you can separate the cars based on the color, right? So those are categorical variables, essentially. And we have all the values there. So one thing to note is if the totals are not there, it is here for demonstration's sake. If it's not there, you have to first find all your totals, meaning find the total of how many foreign cars there are, how many domestic, how many red, how many black, how many silver. What is your sample space? The sample space, you always either take the sum of the row, the bottom numbers, or you can just take the sum of the last column, like 21 plus 34. Same thing as saying 23 plus 14 plus 18. Okay, if one car is selected at random, find the probability that the car is foreign. Right, so for part A, we're doing the probability of foreign. Well, look at your table. How many foreign cars are there? There were 21 foreign cars. How many total cars were in J&S auto lot? 55. So you take 21 divided by 55 and you round this off to 4 decimals. Thank you. Have a good one. See you tomorrow. What's 21 divided by 55? You got to do it 4 decimals.
.382.
4 decimals.
0.3818.
Thank you. 0.3818. And that's it. Probability of foreign. How many? Okay, that's it. Let's look at part B. Part B states probability of silver. Well, first you look at your how many silver cars there are, and you divide it by your the number of outcomes you have. So how many silver cars do we got? 18. What was your sample space? 55. So you do 18 over 55, which is approximately 0.3227. I think there's actually a 3. What came after the 2? A 7?
Yeah, because it goes, oh yeah.
So the 7 tells the 2 to go up. Yep. So 0.3273. Okay, now part C, got to be a little careful here the way it's worded. It says find the probability now that the car is foreign and silver. So when it speaks about that one car is remember, we were dealing with one car being selected at random here. And now it has to share both of these characteristics, foreign and silver. Are we looking at specifically the totals here? No, you have to look at wherever the two variables intersect that. So how many foreign cars were silver here? 10. That's right. You look at when the two values, the two variables intersect. So foreign and silver, put it together as a probability, it's going to be 10 out of 55. And if you want the decimal approximation, it should be 0.1818. Any questions? So problem 17.
Why is it not 10 out of 2?
I didn't say given. But guess what? I'm going to say it very soon. So just to show you. See the difference? In problem 18 now, I'm going to use the word given. Problem 17, I didn't use I didn't use that vocabulary at all. Okay. Are we all good with problem 17? Straightforward. All right, now let me complicate it a little bit. That's right. It's like playing it's like watching Dragon Ball Z. For those that watch anime, it's like when Goku goes from regular, yeah, that's okay, and he goes to Super Saiyan. He increases his power level. That's right. We're increasing the difficulty of this problem. Okay, so same problem, same data set, rather. Same data set I use. I didn't change none of the numbers. Same data set. But now, there's key words here. It states that if one car is selected at random, find the probability that the car is foreign, given that it's silver. The car is silver, given that it's foreign. And the car is black, given that it's domestic. Okay? So when I look at part A, B, and C there, what is the key word that you see there? The key word. There's a key word that tells us what probability formulas to use. What's the key word? The word given. The word given implies conditional probability. Okay, so let's write out the formula. I'm not actually going to solve this problem using the formula. We're going to do it in like exactly with the formula. I'm going to do it intuitively. So the word given, when you see it, it implies conditional probability. Edwin, you're there? You're going to see this tomorrow. Yes. So for conditional probability, the formula states the probability of B given A, right? That bar, when you see that bar there, that means given. And we say that the probability of B given A is equal to the probability of A and B over the probability of A. When I'm dealing with conditional probability and I have this formula, I use it intuitively. I prefer using solving conditional probabilities based off of the sentence. What we're computing essentially is the probability of event B occurring given that event A already occurred. Look at the way that the occurring or the word occur is being written. There's two different tense here. When I say already occurred, I wish I had Cardi B come in here and she could have did that R for me. But if you look at the word occurred, is it present or past tense? It's past. That's past tense. So when you're dealing with past tense here, that means that the event A, the first event A, already went by, okay? Now, event B is occurring. So that is present or future. And this is, again, your second event. So in other words, the second event, which is your event B, depends on the first event. Okay. So I'll show you how to solve this intuitively. Part A, what X does first, the car is forward, given that it's silver. I'm going to use the probability notation, but just remember that the bar stands for given. So part A, probability of foreign given silver. And I can use this notation. This is all fair game because if you look at the word given, by the way, anything that happened in the past comes after the word given. Any word that or any phrase that's before given, that's what we're trying to figure out. So if you want to compute the probability of foreign given that the car is silver, what the formula is going to tell us to do is look at your table intuitively. How many silver cars are there? What's the total number of silver cars? 18. Out of the 18 silver cars, how many of them are foreign? 10. Hence, you get 10 on top, 18 on the bottom. Again, how many silver cars were there? There were 18. Out of the 18 cars, how many of them were foreign? When I look back at the table, it was 10. Now, let's look at part B. We're gonna ignore the rounding part for now. I think we got that part down pat. It's more or less trying to understand this formulas. Look at part B. We have the car is silver given that it's foreign. It's worded almost the same as part A. So do you think that the answers are going to be the same? No, it's not, right? The question is why? Well, which event comes first in part B? Silver or foreign? Foreign. If foreign comes first, when you're using the formula B and A, then foreign will be which letter? B or A? A. So it has to go after the given bar, which means that silver goes first, right? If you look at part A, it was the other way around. Foreign given silver. Now we're doing silver given foreign. So the way you answer this question is you ask yourself, okay, how many foreign cars were there? And then out of that many foreign cars, how many of them were silver? So how many foreign cars we got? 21. Out of the 21 foreign cars, how many of them were silver? 10. So you put it together. Probability of silver given foreign is 10 out of 21. Let's try part C. So I'll do part C here somewhere. I'll do it on the bottom. What I want you to do for part C, where it says the car is black given that it's domestic, I want you to write it out in the probability notation. Okay? So what would be your event B? What would be your event A?
A would be domestic.
A would be domestic.
B would be black.
B would be the black. So when we use our formula, it's the probability of black. The bar stands for what again? Given that is domestic. So look at your table. How many domestic cars were there? 34 domestics. And out of the 34 domestics, how many of them were foreign? Sorry, my bad. Out of the 34 domestic cars, how many of them were black? 11. And that's the final answer. Again, it's not technically the final answer because we had to do the decimal stuff, but I'm ignoring that for now because I wanted to focus on the formula, how I use it intuitively. Did I actually, plug numbers in? Like, you look at the formula, did I did any heavily calculations? No, I just answer it intuitively. You ask yourself 2 questions. How many of blank do you have? And out of that blank, how many outcomes do you have for event A? And how many of those, and out of all those outcomes, how many of them are in common with event B? Okay. We're good on conditional probability. How's everybody in the chat? We're good on this one? Okay. We got problem 19 and 20, and we're almost done for the show. So again, I'm using the same table, but now there's a key word in this problem. I only can do one part. I got lazy here. I was doing this like at 2 a.m. One night, and I was like, you know what? I'm gonna stop at part A. So part A states, if one car is selected at random, find the probability that the car is domestic or red. So when you read part A, what's the key term there? The word or. When you see the word or now, or in probability stands for which probability rule? Addition. There you go. Or means that we're going to use the addition rule. So the addition rule states that if you have the probability of A or B, it's equal to the probability of A plus the probability of B minus a possible intersection between the 2 probabilities. So I'm going to directly substitute A and B with domestic and red because that's my events, right? We have, I thought I would need more workspace for this one, but I did it. We have the probability of domestic or red. So this is going to equal to the probability of getting a domestic car plus the probability of getting a car that's red minus the probability of both. When I say the word both, I'm implying that the car is domestic and red, a red domestic car. But I just summarized that as both. Okay, so how many domestic cars are there? 34. But we're going to write it out as a probability, right? So we take 34 and we divide it by what number? 55. Plus the probability of getting a red car, which is 23 out of 25, 55, sorry, minus the probability of both. Is there any red cars that are foreign or any foreign cars that are red? Yeah, how many of them are they? 8. There were 8 red foreign cars. Okay, now there's a cool thing about fractions. Look at your bottom number. The bottom numbers, your denominators are all the same. So you just add or subtract the top. So you take 34 plus 23, then subtract 8. Oh, sorry, my bad. I said something, I subtract by the wrong number here. It shouldn't be red and it shouldn't have been red and foreign. It should have been red and domestic. So the intersection is 15 out of 25. Okay, but yes, you take 34 plus 23 now and then subtract 15. No, it can't be 34. 42. So you get 42 out of 55. And then you follow the rounding rule. The rounding rule says to do 3 decimal places. So if you want to check that out, it would have been like something like 0.76, I think 4. If you were to do it, 0.764. Questions? I might use the workspace for this problem for problem 20. But anybody have any questions on the addition rule? Ooh. Oh, great. All right, one last one to hit the road. Problem 20. So the one addition, the one rule that I haven't really went over thoroughly for probability is the multiplication rule. This is an example of the multiplication rule combined with the complementary rule. So let's look at this problem. It states that it's reported that 27% of the US adults get enough leisure exercise time to achieve cardiovascular fitness. If 3 adults are selected at random, find the probability that all 3 get enough daily exercise, none get enough daily exercise, and then part C states at least 1 gets enough exercise. So the way that this is being computed is as follows. First of all, look at your percentage. When you're dealing with the percent and probability, it's best to work with decimal numbers. So 27% as a decimal is what? 0.27. Now, let's say that if I just had to select one person at random. If I select one person at random, what is the probability in terms of as a decimal number that the person gets enough leisure exercise time? If I select one person, just one, based on the data, what can you say? If one person was selected at random, right, just one, not 3, just one, for the moment, one person selected, what would be the probability that that person, yeah, it would have been 27%. That's right. Well, no, I don't know what you meant by that, Lauren. Sorry. Part C is just 20%. No, part C is not going to be just 27%. I just said if one, exactly one. If exactly one person was being selected, then it's going to be the chance is going to be 27% or 0.27. Here's another example, another situation of this. How many of us are in this room? There's, well, excluding me, talking about the students, is 8, right? There's 8 students. So the probability of selecting one student at random would have been 1 out of 8. Like if I want to select Martha, that would have been 1. The chances I select Martha would have been 1 out of 8. Okay, now, if I wanted to select a second person, it depends on the fact whether or not, if there's any dependence. Meaning, let's say that I select Martha, right? I told her to stand up and then sit back down, right? She stand up, she sit back down. Then I said, okay, I'm gonna select another person. Or sorry, I'm gonna select a second person. Martha can get reselected because I told her that whoever gets selected, they stand and they sit back down. Long story short, with the multiplication rule, it depends on the fact that if the 2 events are independent or dependent. And if the events are independent, which they are in this case, they're independent events because nothing's getting replaced, or one event doesn't depend on the other, then the multiplication rule tells us that you can take this decimal number, 0.27, and you can multiply it many times. Wait, that allows me to do this? Oh, that's kind of cool. I didn't know I could do that. Smiley. I didn't know that. I could touch the screen and do all that stuff. Okay, so part A. If you wish, in short, if you want to compute the probability of all 3 adults, just simply take 0.27 and multiply it by itself 3 times. It's essentially combining a counting rule with the multiplication probability rule for independent events. Long story short, when you multiply this all out and you round it to 3 decimal places, you get 0.030 or 020, sorry. Sounds good? Okay, now let's think about this for part B. Part B states we want to compute the probability that none of the people none of the 3 people being selected gets enough daily exercise. So if 27% of the people gets enough leisure time to do exercising, then what would be the case for none? What would be the percentage for none of the people? Or sorry, if 27% is the probability that you have, again, or let's think about it with a coin flip. What's your name again? Yeah, Sanjita. If Sanjita, say we did a coin flip, which side of the coin do you want? The heads or the tails? Heads. What's the probability of her getting the heads that she wanted? 1 out of 2. What is the probability of her not getting the heads? It will be 1 out of 2. So because I'm saying the word not, it's a complement. So what would be 27% or the complement of 27%? 73. So if you want to compute the probability of none, meaning that the first, second, and the third person do not have enough leisure time, then you would have taken 0.73 because it's the complement of 0.27. And you would have multiplied 0.73 now 3 times. If you do and round your answer to 3 decimal places, it's 0.389. Done. Okay, let me just show you a quick formula for part C. It's really simple, but I just want to show the breakdown of it, and then we'll wrap it up. So, by the way, how many adults were being selected at random in this problem? 3. So the outcomes that we can get is that we see that all 3 adults can get enough daily exercise. There's the case where none of them, which implies 0. We could have the case where exactly 1, exactly 2, and of course all, right? So we see probability of 0 plus the probability of 1 plus the probability of 2 plus yada, yada, yada. Let's just say probability of k. If I add up all of these probabilities, right? If I add them all up together, the sum of the probabilities approximately should be equal to 1, right? Because of rounding rules, sometimes you can get something a little off, but it should be very close to 1. Now, if you're talking about the at least 1 case, what does at least 1 would imply? Right? If you're looking at least 1, that implies what? Well, look at the word look at the phrase at least. Yeah, Lauren, thank you. 1 or more. So if you want to compute the probability of 1 or more, meaning at least 1, which is this portion of an equation, at least 1, then I can rewrite this as follows. I can say the probability of 0, meaning that it never occurred, plus the probability of at least 1 is equal to 1. And if you want to get the probability of at least 1 by itself in the equation, then just subtract by the probability of 0 on both sides, right? So this will give us the probability of at least 1. Sorry. Is equal to 1 minus the probability of 0. So probability of at least 1 equals 1 minus probability of 0. But we computed the probability of 0 on this problem. The probability of 0 on this problem was the result of part B. It was 0.389. So you just basically plug that value down here. You get 1 minus 0.389. And that will give you 0.611. This is something that you would see when you're going to start doing, I think, binomial probability distributions, I think. You'll see this a little bit more. But that when you do those, you can do, I think, like at least 3, at least 4, yada, yada, yada. The probability of at least 1 is a little bit more special. It's always the whole thing minus the probability of it not happening. Whatever your event is or your procedure. And that wraps up my review, everyone. Whew, what a review. 3 hours. Let's make it 3 hours. 3 hours and 20 minutes. I start about 2:05. Alrighty, I hope you guys enjoy this. Mr. Merrill, you raise your hand. You have a question?
Yes, Professor, I want to ask what review is that? Because I came late.
What, problem 20?
No, I said that's the questions, and the 20 questions is for the what's test review.
That's right. There was 20 questions in this review. You're welcome, Kanisha. Mr. Merrill, there was 20 questions in my review. The recording for this session, I am going to, well, Raphael is going to, he's going to upload it to our website. And this will be blasted to all students in 132, probably sometime on Sunday. I have one more workshop as well on Saturday. I'm going to repeat the whole thing again.
Okay, so that's related to our middle term exam.
Yes, very related. Should be.
Just the same, almost like same kind of question like that, right?
That's right.
Oh, okay. Thank you, Professor.
Alrighty. Somebody else have a question? Yeah, go ahead. Hutchinson? Yeah.
Yeah, so I just wanted to ask you about the workshop you'll be having on Saturday. Will it be different questions or the same set of questions?
I might just use the same exact questions. But what I'll do is I'll probably begin with like question 10 first. I'll do like the bottom half because that's easier to do.
Okay.
We'll probably do that first and then I'll go backwards. Because you guys can see that when I did the statistical and critical thinking part, that part slowed us down. After I got through the statistical and critical thinking section of my workshop, things went much faster for us. But I basically did 4 chapters today. So, you know, and doing 4 chapters in like 3.5 hours, that ain't bad. Yeah?
I put 20, 27, 3 times.
Did you put top plus? Did you get like 0.81? Oh, you got to round. You got to round it to 3 decimals. So you got like 0.019. So the number that came after the 9 made it become 0.20. You rounded 0.19 to 0.20. Yeah. You guys are welcome, Bernie. Bernie, you're welcome. You're welcome, Juana. Hope you say your name correctly. Yep. So if you guys don't have any questions, you guys are definitely free to go in the meeting. We have your attendance automatically recorded when you joined, and we have it all saved. So we have the link that you saved for the meeting as well. Yeah.
When will the video be uploaded?
Raphael, when do you think the video is going to be uploaded to the site? Raphael? Oh, I forgot.
Thank you, Professor. After the Saturday, do we have any other workshop?
No, after Saturday, no more workshop.
Oh,
not for now, at least.
thank you. Thank you.
Oh, Raphael, when do you think the recording is going to be uploaded? Tomorrow morning. Tomorrow morning. Oh, the reason why, I think Raphael teaches tomorrow morning. Well, not tomorrow morning. He teaches like in half hour, so I gotta go see him soon. I gotta take his spot. That's right. Yep. I'll be up there soon. Anybody else? Any questions? Yeah, O'Neill?
I don't have a good vision for the night.
A good vision? A picture?
Yes, I don't have a good.
Okay, you can take a good picture. Let me just move the chat thingy out of the way. Yep. I forgot your name already. Sanja? Yeah. Sanjita, my bad. Sanjita. Which question?
It was the one with the me.
Question. Do you have your picture, O'Neill?
Yeah,
Okay, you should have said thank you.
thank you, teacher.
Put me on 13.
13?
Yeah.
Sure. Wait, let me just take, I don't need this part anymore. There you go.
Thank you. There.
You're welcome. Oh, by the way, if you guys don't have any questions, you guys are all free to go.
Thank you, Professor. See you Saturday.
See you Saturday.
Mhm.
Problem number, the mean median mode problem. That's
The
problem
one
9.
where The answer was like.
Oh, 8.
5, 6. Yeah, that one.
Which one was the confusing one?
It was the mid-range part, because even when I did it by hand, I'm like.
Oh, what's 71 plus 42? Maybe I did this wrong.
It's 113. right?
Yes, I did this right. So you did 113 divided by 2. So you do it in your calculator, do the addition first, then divide by 2 after. Because it does PEMDAS. The calculator would say 42 divided by 2, you get like 21. And then it adds 71, you probably got 92. So do it one step at a time. Yep. Already. My bad, Martha. Anybody else? Any other questions? All right, you guys are all free to go. Yeah. Yeah, sure. Go ahead. I brought it back. I know you stepped out. I'm from Jimmy's class, and for the attendance. No, Kiara, you're fine. We have it recorded. You're good, Kiara. Dark one, you're welcome. Sorry, I mispronounced almost half the people's name there.